Okay, so what I want to do is to welcome all of you to a topic, the final topic known as correlation and regression. And to do that, we shall still resort to the gene data set. You already know about that data set. I want somebody to read the first bullet. Who is available to read the first bullet? Because we are going to use that data set to make home the point. Who can read the first bullet?
Doug, I'll read.
Go ahead.
You are writing a journal paper, thesis or project or dissertation entitled Determinants of Demand in the Alcoholic Beverage Industry in Ghana. Impact of Location, Occupation, and Religion. Albeit previous studies on such subjects exist, they have not considered the potential effect of location and occupation. You may justify this with reference. Few studies have considered religion, but not included Buddhist to the best of the author's knowledge. You may have to also identify other gaps, previous studies employed on ANOVA and correlation, not regression, etc.
All right. Okay. I think you were a bit in a rush, but it's okay. So normally, that's what you would do. Some of you may have already started your research, and you are probably already doing that. One of the first three things I would encourage you to do with your research is that know the gaps. You should have at least three gaps. Don't say that people have done in the US and they've not done in Ghana. Don't just say that traditional models are using this, when in reality, you don't know what the traditional models are. You have to say that traditional models such as A and B have been consistently used, but people have not employed machine learning models such as A, B, D, C. And why should they have to do that? You justify. Okay. So some of the gaps are, you can make a conceptual gap, theoretical, which is normally unlikely. You can make a methodological gap. That is very likely. You can add to the body of methodology. You can also make a policy gap. For example, you believe that by applying the thing to default, loan default, or fraud detection, or stock price prediction, or any particular area, you are going to help stakeholders, managers, regulators, government, people. So you can coin that policy gap. And then from all these gaps, you need to now come up with a contribution. So the thing that must stand out are your gaps, your objectives, and your contribution. These are key. So from the problem statement, you usually will state your contribution. So the contributions are always coming from the problem statement. And the problem statement is the same as the gaps. What is there that is not supposed to be there? Or what is not there that is supposed to be there? And then from the research questions, from the objectives, you create your questions. The questions are the same as the hypothesis without a question mark. The hypothesis is a statement, and then the research questions are question marks. Okay. Based on that, you now gather data to address the question. So every research question you ask, you got to have a methodology, a particular technique you're going to use to answer that question. It must be precise and concise, explicit. Okay. Now, so let's assume you got a book to data set. You know all about this data set, so I'm not going to explain. The data set is also here, okay? As a reminder, this is a video, a long time video on the Burkutu data set. Some of you might remember, some of you might not remember. Okay, but who has been able to watch that video? Because it's a very popular video. will remember that for a while, and that is a drink, the company that we are looking at here. Now, we've already looked at cross tabulations, we've already looked at visualizations, we've already looked at numeric factors and all of that. What we want to do now is, in fact, we've even examined some hypotheses. We are going to generate the data set. So this command, I want you to use this command to generate your data set. Okay. Now, if you have to run this and it doesn't show, then you have probably lost some packages. So you got to let me know. Okay, you got to let me know. I'm going to run this and then see. Okay. So the idea is it's supposed to be loading. The star means that it's trying to load. Now, if you could remember this data set, you will notice that which variables would you say are categorical? Location, occupation, and religion. Which variables are numerical? Q, P, C, M. Which variables are float? This is just a quick reminder. Guys, quickly help me here. Which variables are float?
Float, M is...
And potentially, which other?
P.
And potentially, which other?
P.
P.
Which variables are Boolean? Which variables are Boolean?
Shop.
There's no Boolean. Which variables are integers?
Q and C and potentially P.
We've already classified it as a float, as a potentially float, and then you say that it's potentially that. Which variables are characters? Which variables are characters? You don't know your variables.
Location, occupation, religion. Shop.
Which variables are dummies? Which variables are dummies? Okay. So one of the first things you want to do is to visualize the correlation matrix using heat map. And I know you guys have learned a lot about heat map. Okay. So you can choose any particular heat map you like. Okay. It depends on your requirement. And heat maps are very, very useful. It's just a picture understanding. But today I'm going to show you something unique heat map that people hardly show, which is really, really good, especially in a practical analysis. So if you are doing your research and you want to generate any heat map, this one is superb because it encapsulates both the correlations as well as the significance. Okay. Now, for you to be able to generate heat maps, ideally, your data must be numeric. It has to be continuous or discrete, numerical, not categorical. In fact, even if you're going to be generating categorical, don't do it. Sometimes R will allow you to do that, but don't do it. Don't use it. Okay. Sometimes you can use them for categorical variables after quantifying them or numericalizing them. Okay. Sometimes, if you want to show categorical variables, you may rather show the counts. That is how many of the firms are urban and how many of the shops are rural. You can show that. Or sometimes even the averages. But if the data set has some extreme values, okay, like outliers, okay, or if the data is very sparse, I've made a point here that the heat map might not be as effective without pre-processing or normalization. If you are dealing with text, images, okay, and other forms of unstructured data like what we have here, they are not directly suitable for heat maps at all. You don't even have to think about heat maps for such ones. So to do the heat map, you need the CMON and then the matplot library, the pyplot. And you can see that this column here, I've indicated that you should drop the categorical variables, or even any variable you don't want. It might not be categorical per se. For example, year. Year is not categorical per se because they're actually numbers. But we have included it because we don't need a correlation as far as year is concerned. So this column will drop those variables. Then we create a new data set from this DF data set. We call it DF filtered. Okay. And then we ensure that what is left is only numeric variables here. And then based on that, we indicate that they should include the numbers. After that, you can use this command to create your correlation matrix. If you want it to be of a certain figure size, I use 6.4, you can use any other. Okay. And then you can show that. The SNS is the actual heat map. Okay. This are not, I'll show you an example very soon. So you can see this is the first one. Let me run that. And then let's see the result. Why is the thing slowing down quite a lot today like that? Normally it's quick. I don't know why it's taking so long today. Then I can imagine that the others are not going to show. Okay. Anyway, so you can see that I have written the annotation, annotate to be true. That means that the right part, the right diagonal part will be showing. But if you don't want the right diagonal part to be showing, you can make this false. It will look like exactly the one that you normally have in Excel. Oh, what happened? Let me undo that. Unless it's not this command that does that. Okay. Okay, so potentially this command will not do that. I have a different one I'll use there. And here, the line weight will show the weight of the lines. It is a tight layout plot, so it's not too big, as you can see here. And from here, we're going to address some questions. So this is just one way of generating a correlation, heat map. But please look at it carefully. You will notice that we'll come back to the individual variables and talk about them. But if you look at it carefully, you will notice that this is just mere correlation, doesn't tell you the p-values. Okay, you can tell me there's a correlation between quantity demanded and price. We all know that the relationship between quantity demanded and price, is it positive or negative? Correlation-wise, is it positive or
Negative.
It's negative, okay? And you can see that here, in the correlation here, you will notice clearly that the relationship, this thing is really slow today, honestly. Okay, this is really negative, okay, and it is high, close to 1. So it goes to confirm that that part is shown, but is it significantly negative? That's a question. It is negative, but is that significant? Okay, so to do that, you would generate the correlation with p-values. And most studies don't do that in heat map. They take it to R. R does it beautifully, but here you can use this command to do that. So how do you do that? Well, after importing the usual ones, I've included SciPy here, okay, as a command. The same thing, it could be a continuation, but I've just repeated everything backward. Okay. This will create some empty cells, will generate the correlations here, and the second one will generate the p-values here. So I've created a command that will create a correlation, which is this part here, as well as the p-values. Okay, we are using Pearson's product moment correlation coefficient. That's why you can see that I've written Pearson R. That is Pearson correlation there. And then this will print out the result, both the correlation as well as the p-value. Let's do that. And this is what you get. Okay, you should check yours to be sure that you are getting the result. Now you can see clearly from here that, oh, by the way, I indicated that the correlation, I want it in 2 decimal places. So this is 2 decimal places. But then the p-values, I indicated that I wanted it in 3 decimal places. There's a reason why. Because if you look at the p-values here, I will give you all of this in an exams. Yeah, I'll generate these results for a bigger data set, and I'll ask you multiple questions on that. So if you don't understand anything, else, you can see that there is a number for this. So each information above has a corresponding p-value below. So as an example, who can tell me the correlation between quantity demanded and complement price? C. Who can tell me the relationship between quantity demanded and complement price? What is the correlation? It's 72, okay? It's 72%. And when you check the p-value, you will notice that the p-value tells you that that relationship is significant at 0.1%. 0.1%. Take note of that. That is the best of correlations one can actually deal with. Now, this is the other bit. That is the pretty one. I like this pretty one because this correlation, and again, look at it here. We are plotting the same heat map, but then inside every correlation, I've also included the code that will generate the p-value straight on. So you can see that the correlation between, of course, when you show the results, you get this. The correlation between, but I can change this. Let me change this and see. You use cool warm. Just want to see how the results look like. So you're going to get a correlation, and for each correlation coefficient, PV metrics. Okay, let me just run this. It looks like I didn't run this first. Okay, there you go. So if you look at this, you have the correlation between quantity demanded and price to be negative 0.87. And the p-value has been bracketed, telling you that that very correlation is significant. Okay. So if it is significant, it will be determined by the p-value. And how do you know whether it is significant? When the p-value is less than 5%, it's significant. Now, in this case, all of them are significant. But it will be good to indicate significant at what level. And there are four major levels: 0.1%, 1%, 5%, and then 10%. In this context here, what you're seeing here, they are all significant at 0.1% because they are all almost zero. So that is how we generate a correlation with p-values here. Every aspect of the code is clear. Unless you don't understand something, then I'll explain. Okay. All of these are correlation. What is correlation? Correlation is causality. Correlation is establishing the relationship between two variables. Correlation has to do with association between two variables. And the association can be positive or negative. They cannot, if it is positive, you can also have strong positive or weak positive. If it is negative, you can have strong negative or weak negative. For example, when you look at that of quantity demanded and price, it is positive. Sorry, it's negative, and it is strong negative. It's negative, but it's strong negative. Now, if you look at M, and Q, it is positive, okay, but it is moderately positive. It's not as strong as the other ones. So that gives you an idea of the strength of the correlation. It's like when somebody says, I love my husband, I love my wife. Okay? The strength of the relationship will be determined by the value of percentage that the person would give to that relationship. Okay, so now we go to this question. And I need your answer here because the answers are not provided. Which two pairs of variables exhibit high correlations with the response variable? Who can give me the answer? This is an exam question. Which two pairs of variables exhibit high correlation with the response variable? Let me pick on Albert. 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 Anybody who is unable to comment, I'm going to give the person a negative mark.
Yes, Doc.
So you're alive, right?
Yes, please.
And now I say I'm going to give negative mark before you say yes, Doc.
No, the line was breaking, so I didn't hear you.
But you could have at least responded. I called you 4 times. You could have at least responded.
Sorry, Doc.
Well, you got to be, because it's a deliberate, calculated attempt to sabotage my intelligence. So answer me the question.
Okay. Yes, they're mostly collinear is P and C. Sorry, Q and P. Mostly positive collinear with a collinearity of 0.87.
That's wrong. Let me note that down. Let me go to David. I'm going to give negative to everybody who actually misplaces his answers here. David, I'll make sure that everybody will be answering so that everybody speaks. David.
Hello, sir.
Yes.
It's MC. Sorry, CQ.
Have you seen the question I've asked? This is a question. In case you can't see, this is underlying question. Which 2 pairs of variables exhibit high correlation with a response variable?
Just one. I'll still go with CQ.
CQ.
Yes, please.
Okay, that is wrong. Let's go to the next person. And that is David Oku. Yes, David.
Hello, sir.
Yes, go ahead. Sorry, David, go ahead.
Yeah, I would go with P and M.
It's like you are choosing a different one because they got it wrong, or what? The way you said, I'll do it.
No, sir.
Are you selecting a different answer because they were wrong? Or you know exactly what you're doing?
Not entirely, sir.
Okay, so which one are you choosing?
P and M.
P and M is wrong. Which 2 pairs? Remember, the pair, you got to have a first pair and the second pair. Okay, let's go to the next person. G-Body.
Okay, so I'll choose Q and C and then C and Q.
That's wrong. Let's go to David. No, David Bedu.
Sir, I already answered.
Oh, yeah, you are. Thank you. Yourself. Forgive.
Doc,
Yes.
so the pairs are the where the
First pair and the second pair. And why?
So P and Q are
Why?
one pair. Why? Because they have a high correlation of
Mention
87.
numbers, exact numbers, full numbers, everything.
So they have high correlation of 87%, but negative correlation. That's the P and Q. And then P and C also has a high correlation of 0.74. That's 74% and significant.
Your second one is wrong. So your first one is correct. I'll buy that. Let's hold on to that. Okay, that saves you. Okay. Let's go to the next person. Hubert. What is the second pair?
So I'll go for P and Q.
But that's what he has already done. And I said that is sorted. I want the second pair. Watch the words. Read the words very carefully.
So I'll go for P and C.
That is wrong. Okay, because that was also said, and I said it's wrong. Let's go to Jessica. Jessica Bosso.
Dog, when they are done, I will amend my answer, the second one.
Yes, sir. Sir, I'll go for P and Q and then Q and C.
Tell me the numbers. Always mention the number. Don't just leave it ajar. And if the numbers are positive and negative, indicate.
Yes, sir. P and Q of -0. Yes, sir. P and Q of -0.87 and then Q and C of 0.72.
Very good. The rest of you who don't know, put that in your document here. Put it down here so that you know. So the first one is Q, and you got to mention them in order of which is highest, because the question was high. So you got to mention the highest one. Okay? So you say Q and P. Then you put into bracket -0.87. The absolute value is what you focus on. But when you are writing, you write the negative as well attached to it. Then the second one in the order high is Q. And remember, why Q? Why are we taking Q? Because the question says response variable. The response variable is quantity. So that is the response variable. That's a Q. Okay. And you got to look on that row, this row here, and you see that the next important one is 0.72, not a 0.61. So that will be Q and C. That is how you answer that question. That is why the question says justified. This is an exam question. I won't lie to you. That you will get similar one with a different data set. Okay, if you don't understand, you can ask. Next question. And we go in the next person order. What does that tell you in terms of the predictive potential? So the answers that have been given are Q and P and Q and C. What does that tell you about the predictive potential? Joseph, Ernest. What does that tell you about the predictive potential? Joseph.
Hello, Doc.
Go ahead.
Yes, please. For P and C.
All right. So what you didn't say anything. So what this means, now I'll wait for another person before I go and see if I can give the answer. Hey, Rabina, tell me your answer. What does that tell you about the predictive potential, Rabina Benson?
Sir, so I think just to confirm, I think we're looking at between P and Q and P, and then Q and C. Okay, so Aliza lets me know that the Q is highly, at least the P and then the C values would help predict Q better. I'm not sure. Yeah.
Say that again.
So they are significant to predicting the value of Q.
Good. At least what it means is that they've got a very high potential of predicting Q. Okay, as to whether that is true, we are yet to find out, but that is what is very good. You've made some attempt. And let's go to what's the name of this person? Fanuel. Fanuel, are you there?
I'm here.
Good. So the next part is, are they statistically significant? And tell us why.
Yes, they are
Why?
significant. Because a low P value indicates that the corresponding predictor is statistically significant.
Explain. Explain. Should I give you the negative too? This is your exam, so. Funnel.
Yes, sir.
It looks like you haven't been attending my class, have you?
Yes, I do.
And you don't know how to do it. I mean, this you have done even in other modules already, haven't you?
Yes, please.
And you're still struggling? Next person, get ready. Joshua, Richmond. Alec William, Richmond, Seth. All of you, get ready. Theophilus. All right, okay, finally you're out. Let's go to Joshua Alec William.
Yes, the p value for the Q, the p values for the Q is it's recorded, it's 0. So that makes it significant because it is
Why
less
does
than,
that make it significant?
because it is less than 0.005. So if it is less than, what I know is if the p value is less than 0.005, 0.05,
0. What?
0.05.
Okay, I had 0.005.
Yeah, that was a mistake.
Okay, go
If
ahead.
the p value is less than 0.05, then it's significant. And if it is higher, then it's not significant. So since the p value recorded there is 0.0, I think it should be significant.
Very good. You've made a very wonderful attempt. Okay. Now the next question says that which two pairs of variables are mostly multicollinear? Now I'm going to define multicollinearity for you. Take your pen and paper and your book and write it down. Be deliberate and write it down. Be deliberate and write what I'm going to say down. Maybe when you started this, you don't have your pen, you don't have your book with you. Now look for it, get it ready and write what I'm going to say down. Because that's the only way you're going to answer the next series of questions. What is multicollinearity? Multicollinearity usually exists when two independent variables are so highly correlated, they are so highly associated to the extent that it becomes difficult to disentangle the partial effect of one from the other on the dependent variable. It happens when two independent variables are so highly correlated that it becomes difficult to separate the partial effect of one from the other on the dependent variable. That is multicollinearity. Got to do with independent variables. It's got to do with the features. It's got to do with the regressors. When they are so associated with each other, multicollinearity can exist. I think I've taught you guys that before. I hope I have. Anyway, so that's multicollinearity. So looking at what you have here, which two pairs of variables are mostly multicollinear in this context, in this numerical information that I've been given? Which two pairs of variables? Which one? Which one, Agoda?
Yes, sir, please, I'm here.
Yes, answer the question.
Please, is the first pair is the P and Q, which is 0.87.
You did not write the definition of multicollinearity that I just gave. You didn't write it. So maybe what you should have said is that, Doc, could you please repeat what you said? But you didn't say that, which means that you understood it. Because if you wrote it down, you will not give the answer that you gave. Let's go to Seth. Seth Sebekusi.
Hello, sir. Please, I will choose C and M. I'll choose C and M in looking at the relationship with the output variables here.
Why? Tell me why.
Because C is 0.72 and M is 0.61.
No, there's nothing called C is 0.72. No, that's not.
Okay,
Correlations are two pairs, so I don't know.
CQ is 0.72 and MQ is 0.61.
But if you can remember the definition of multicollinearity, you will not give that answer. You will not. You see, I deliberately decided to let you guys talk to see those who have been paying attention. Theophilus Crunchy.
Hello, sir.
Go
Hello,
ahead
sir.
and answer the question.
Hello, sir.
So it's P and C. P and C because P and C has a correlation of 0.74, which is close to
Not
1.
0.74, it's negative 0.74. Say that.
Negative 0.74.
Mm-hmm. So
and because it's close to 1, they are highly dependent on each other. So there's strong correlation between P and C.
But there's strong correlation in all the others as well, right? So I want you to relate what you're saying to the question here. Relate it to the question. Why did you choose that in relation to the, are you answering the question or you were?
Yes, sir, I was answering the question.
So say it well. These are my questions I'll give you. These are the sort of questions I'll ask you. I saw a hand raised. Whose hand was that? Yes, forgive.
So, Doc, is P and C because the
Mention
negative
the number before you say because.
So the correlation coefficient is negative 0.74, which is approaching 1 as it said. So there's high multicollinearity between those two independent variables.
Okay. So what I needed was for you to say that it is the highest than all the existing ones. Because if there was another one, that was 0.82 in the independent variable section. By the way, those of you who are choosing the K was not an independent variable. K is not an independent variable. So any column at the K column section shouldn't have been selected. So if you look carefully here, this column has got K. You can't select it. This column has got K. You can't be. So your area of interest is just going to be this area. They are the independent variables. That's it. That's where you focus on. And that is a situation that I wanted. And then forgive, you gave that last answer. The point is that Before, let me check something. I want to check a certain command. So when you actually look at the result, you will notice that, okay, I'm going to check a certain command that when you look at the result, you will notice that it is the highest among all the existing ones, the highest of the independent variables among all the existing independent. That's why that value comes first. So which is the next pair? Which is the next pair? Because the question said 2 pairs. So you've mentioned 1 pair. Which is the next pair? This question is open before I start again. Otherwise, I'm going to start again. Albert.
C and M, Doc.
Get used to mentioning the numbers, okay?
Okay, C and M, because it has a positive correlation of 0.71.
Okay. So that is what you would have indicated. So just note this. If you were doing your own research, I would expect you, your own thesis, I would expect you to generate this correlation matrix yourself, this heat map yourself with the p-values yourself. Then I would also expect that, because if I'm marking your work and I will mark your work, I would expect you also to explain those that are potentially multicollinear. And of course, those that are least multicollinear. I could have asked you least multicollinear. I've asked you the most multicollinear, but I could also ask you least multicollinear. Okay. Any question on this? I think that if you look at the seaborne here, I use heat map. Heat map doesn't accept corner. Okay? It doesn't accept corner, but this one accepts corner. So look at this. I have selected these same individual variables. I'm going to create the same thing as this, but in a scatter plot matrix. Not a correlation matrix, but a scatter plot matrix. What's the difference? The scatter plot matrix is a graph. It doesn't show the numbers, it shows a graphical representation. So this is a command, it's a pair plot command that you're using. Okay. I've selected some individual variables, QPCM. And so I'm running that. And you can see that the diagonal, I want kernel density estimate, the kernel density graph to be in the diagonal. I can change it to any other. I can use histogram. I can use another thing there. And then I've indicated that I want the corner point to show. So look at it. I want the corner point to be true, which means that I want the corner point to show. Now let me run that. And you see that the corner point should show. It's loading. I think I've opened quite a number of information, so it takes a bit of time. Okay. For some reasons, it still shows that. Okay, let me make it false and see. So you can see that it doesn't show all the cluttered information. You know, for example, if you look at this one here, it shows everything on the top and everything on the down. Normally, it becomes quite complex because it's a mirror image, so the whole thing is the same. So there's no need to show that mirror image. Okay. But when it comes to the graph, you can indicate when you're using the pair plot, you can indicate here. So, okay, so now you can see it that this one, when you say false, it will not bring any, it will bring all the mirror images, as you can see, the left and right. But once you do corner point to be true, it will clear all of the right part of the graph so that you don't have any wahala to show. And like I said, you can change this one to density instead of the KDE. Okay. So this one will have, so clearly you can see that the quantity demanded, this top part here is for quantity demanded. Quantity demanded alone is not normally distributed. But look at the price. Price is almost normally distributed. Look at complement price. Complement price is multimodal at the peak. Okay. It appears normally distributed, but it's just multimodal. And then if you look at the last one here, which is the M, the income. Income is also multimodal. Okay, there are two peaks there, and therefore is also not normally distributed. So that is one way you can have a picturesque understanding of the variables. Now remember, correlation, write this down. Correlation is about association. Regression is about causality. Correlation is about association. Regression is about causality. Correlation does not look at cause and effect. Regression looks at cause and effect. Okay, so now regression becomes a step further of correlation, because correlation can tell you that there is an association between something and something. For example, during Christmas period, and you have sales. Let's talk about food. Those are the Makola market. When they do sales, are sales higher during Christmas or not? Are sales higher during Christmas or not?
Yeah.
Okay. Restaurants. Are sales higher for restaurants during Christmas or not?
Yeah.
Yes.
Yeah. Now, normally you would expect that when people are going to buy the foodstuffs at Makola, okay, which is a major market, and then they are going to cook the food themselves, then they are not likely supposed to go to what? To go to the restaurant to go and eat. And yet, during Christmas period, both of them will increase, sales will increase. So there's a high correlation between purchase of goods at Makola, okay, food at Makola, and then restaurant also, there's a high, increase. So there's a correlation, a positive correlation between the sale of goods at a Makola and the sale of goods at a restaurant. But then it doesn't mean that the one at the Makola is causing the one at the restaurant to behave the way it is behaving. There is no association between the two of them. The two of them are not, sorry, there is an association between the two of them, but there is no causality between the two of them. It's not a Makola one, the rise in sales in Makola, that is causing the rise in sales in restaurant. Neither is there a rise in sales in the restaurant. They are all being affected by something external to both of them. So the fact that some two things are correlated does not mean that they have causality or one is causing the other. And that is a very powerful, important distinction that you got to know, because a lot of people make that mistake, thinking that correlation implies causality. I just hope you understand what I just did. So now, let's look at regression. Because regression looks at causality. Regression looks at causality. Now, there are several types of regression. Our focus is on linear regression. Linear regression. The difference between a simple linear regression and a multiple linear regression is that a simple linear regression has got one feature. A multiple linear regression has got multiple features. That's it. And some of these multiple features can also be numerical or categorical. So remember, in a multiple linear regression, you can have dummies. So x1 can be numerical variable, x2 can be a dummy variable. Remember, the relationship is linear. The exponents are all 1, 1, 1, 1, 1. But then in a polynomial or quadratic, relationship, which is not linear. Oh yes, certain things are not linear in life. For example, the relationship between price and quantity demanded is linear. But a relationship between the size of a company, okay, as a company is growing, as the size of the company is growing, as the size is growing, initially that might increase profit, okay? As the size is growing, that might increase profit. As the size is growing, but it might get to a certain section, diminishing marginal returns will set in. And in such a case, the graph, which is going higher, will get to the peak and start bending. So you now have something like a parabola, a quadratic graph. That is what we mean by nonlinearity. Okay? And in such a case, the regression that you use, which is a multiple linear regression, will not work. So you will have squares, as you can see here. But in some cases, you even have cube. That is, it will go up, it comes down, then it goes up again. Okay, so now it becomes, cubic situation. And there are some situations in life that are cubically distributed in that regard. We'll not look at polynomial regressions. There is a logistic regression as well, which I know you guys have learned. Have you guys learned logistic? Have you learned logistic?
Yes, though.
So you know how to model a logistic curve. You know that. The one who said yes, sir.
Yes.
You're not sure. It appears you are not sure.
Something like that. Yeah.
So why do you say
Something.
yes when you are not? You don't even know what you've done.
No, we discussed about it in the
No,
supervisor.
you have to run it. Like I'm going to run the thing with you. You have to run the model, see the results, the figures, interpretation of the scores. Have you done it?
No, sir, we didn't do that.
Please, when you have not run anything with the software to interpret score, don't say you have done. No. You're really master. All right. So let's look at real life situations. Okay. These are real life examples of regression. So this is an example of a regression you see here, which is, I've put all of them together. This is a multiple regression, but the xi is xij. Xij here means that there are multiple independent variables. So you can have x1, x2, x3, up to x whatever number of independent variables. The j here talks about the independent number of variables. So j can start from 1, okay, all the way to p. So p here is a total number of independent variables. Okay, but it's not the total number of sample size. Take note. The total number of sample size is n. So that is 1 to n. That is the I. The I here is the total number of sample size. Okay, so take note. Now, the element of the regression you should know, beta naught is independent. I've written here for cosmetic purposes. There is no economic interpretation for the intercept, which is also called a constant. It's there for beautification and for prediction. So whenever you need to predict, that is when you need the beta mode. Other than that, you can even suppress it. In fact, in Excel, you can tell Excel that I don't want you to even show me the constant, if that's what you want. What about the error term here? Okay, first, the beta coefficient here talks about the marginal effect of each independent variable on the dependent variable. So here, the y is a dependent variable. That is the target variable. Okay, that is what we are trying to predict. And we are trying to look at its relationship with the independent variables. Each one of these independent variables is trying to influence the behavior of y. Each one is influencing the behavior of y. Remember, there are many of them, and each one is influencing the behavior. Now, who is doing well? Which x is doing well? The rate at which, or the impact of that independent variable on the dependent is measured by the beta naught or the beta j. So the beta j, the coefficients, sometimes called parameters, they're actually parameters when they have not been estimated. So this beta is beta parameters. But once you've estimated them, they become numbers. Once you put them into the software and run the scores, you get a numerical value about that stage. It is known as what? Coefficient. Every independent variable will have a coefficient. What is its job? It tells you by how much, write it down. Write it down. Write it down. It tells you by how much each independent variable affects the dependent variable. Okay? It tells you by how much each independent variable affects the dependent variable. Marginally. If the independent variables are in logarithms, natural logs, then the beta coefficient becomes a percentage interpretation. So it becomes a 1% change in that beta parameter will lead to a certain percentage change in the dependent variable. But if they are not logs, if the independent variable, the x's are not in logarithms, then the betas are explained in terms of just units. What is the error term? The error term is what we call the residual. In fact, there are several other names for it. Write them down. I'm going to mention some of them. Write them down. One of the name of the error term is the residual. It's also called the unsystematic rates. It's the disturbance term. Okay, it is an unobserved heterogeneity. It's got names like stochastic noise, white noise, random noise. All of those are names that are given to that. The essence of the whole regression is to minimize this so that the expected value of this error term, sometimes it's epsilon, is supposed to be 0. That word expected value means the mean. The expected value of every number is the mean of that number. So the expected value of the error term is 0. So we expect that by the time you have been able to establish, between the dependent variable and the independent variable, by the time you have been able to establish the relationship between the dependent variable here and the independent variable there, by the time you are done, we expect the errors to be 0. Why? Because if the errors are not 0, what you are saying is that they are biasing the results. They are biasing the result. So this y here is actual y. So that is actual y, which you have. But then we have a predicted y, which we are trying to reach. There's a gap between the two. That gap is the residual. Okay? So that is the residual. So the residual shows the y you currently have and the y you should actually have. And that is what we are estimating. So if the error is 0, then it means that your actual is the same as expected. Your actual y is the same as expected. This actual y, this expected is also called predicted y. And that is our goal. Our goal is to be able to minimize the error sum of squares here. The errors, some of them are positive, some of them are negative. And in order to remove the negativity, we square them. When you square them, then you minimize the error sum of squares using an optimization. And then that will give you the beta parameters that you're looking for. I don't want to go into those details. I expect them to have taught you those things before. This is just, but those of you who have gone through the games. So let's look at practical examples. Okay, so this is a practical example of a regression model. Okay, this is known as a specified regression equation. Please take note. A specified regression equation, I've asked this as an exam question. A specified regression equation is not the same as an estimated regression model. Let me repeat. A specified regression model is not the same as estimated regression equation. What you see on your screen right now is a specified regression model for wage determination. A specified regression model for wage determination. What is the difference between that and the estimated regression equation? Well, the difference is that in the estimated regression equation, they are numbers. The beta parameters have become numbers. The beta parameters are no longer betas. They are now numbers. In the estimated, take note, write it down. You see, your brain normally would think better when you're writing something. So this beta 1 would have become a number. The beta 2 would have become a number. The beta 3 would have become a number. When they are becoming numbers, this is no longer a specified regression model. It's now an estimated regression equation. Another thing about the estimated regression equation, apart from them having the beta parameters to be numbers, is that the error term is gone. So the estimated regression equation has no error term. Keep that in mind. Keep that in mind. In fact, I have an example here. I'm coming to now start asking you guys. So you can see the bottom one, the last one here. Okay. You can see that in this last one, the wage determination equation has numbers. So the beta naught has changed to 150. The beta 1 has changed to 4. Okay. And now you can see that we have caps on them, which means they've been estimated. And the error term is gone. There's no more error term at the end. That means that you have an estimated equation. I will always ask you to do this. So let's go back here. What is the first one saying? The first one is saying that your wage, your salary is affected by your education, experience, position, and ability. Now, each one of you is going to tell me another factor that can affect wage that haven't been captured here. Anytime you have a possible other factor that has not been captured, it is inside the error term. The error term will capture all other possible relevant factors that have not been included in the specification process in the regression model. So we all know that education affects wage, experience affects wage, position affects wage, ability affects wage. There are other factors that affect wage, but they haven't been captured here, but they are all hidden inside the error term. Who can give me one factor that can affect wage? It must be a relevant factor. If it's not relevant, I'll tell you. So let's start again. People. Linda, give me one. Linda, did your network go off?
Hello, Doc.
Did your network go off? Did you step off and came back?
I rejoined.
Okay, give me one.
I think location.
How? I agree with you, but how?
Maybe the cost of living of a particular environment will make the employer pay you more or less. If the cost of living is high, it's likely that your wage will be high.
All right, good. It's true because people in London are paid more than people outside London. Who can give me another factor? Joseph.
All right, Doc. Please, I also think the company size and its profitability.
No, we are talking about your wage. Your wage. If company
Yes,
size
so
is going to
the
affect
assumption
everybody.
is that, so Doc, if there's a larger company and the company is more successful.
What I'm saying is that it has to affect you and it doesn't affect other people. Okay, what you are saying is going to affect everybody, isn't it? If the company size is better, everybody will be affected positively, right? But then if I have education higher than you, I will get more, you will not get, right? So we are looking for factors that are individual specific. David. I'm the authority here who will tell you that the factor you are bringing is right or wrong. I've done this for over 15 years, so I know all these possible factors. Yes, David.
Job description.
Sorry?
Job description.
Job description will all go into the same way. That is what led to you being employed in the first place. So that would give you the position. So it will enter into the position here.
Okay.
Albert.
Job risk.
Exactly.
So jobs tend to get.
So even in the same company, some people can have a risky job than others. Give me an example of companies that might have a risky job.
For example, industries like petroleums, those that go to the rig.
Good.
Or mining, those in the mine sites, they are dangerous. Like there's a high fatality rate, so there's a possibility. So
it's just like being a pilot. Okay. If you're a pilot, you are in the air, the possibility of you going. So that's why they are well paid. Okay. Have it. Okay, so that's it. There are several other factors that could cause. Somebody spoke about location. Okay. Location can affect it. And sometimes too, your risks. Okay, you guys have mentioned it. Let's go to the next one. Okay, blood pressure. You will all agree with me that the blood pressure of a person is affected by several factors, to be honest, as you can see here. Your age. This was an exam question I once gave. Your age. Because your age, which is different from my age, can determine your possibility of having BP or not. Your weight, stress, exercise, smoking status, your BMI, body mass index. All of these are likely to lead to your blood pressure if it is different from mine. Nobody should mention broken heart. Who can tell me other factors that might be in the error 10 that haven't been captured here? I think I've destroyed it all. Maybe it's, but let's see. There are two more factors.
Prof, your cholesterol level.
Cholesterol level. Cholesterol level. It's not here, right? I agree with you. But it's not here. So yes, we'll buy that. Cholesterol level. HB level. Have it.
Whether you eat late or not.
It's all part of the stress or exercise. Now, Kofi Edu. David.
Genetics.
Excellent. I love that. Hereditary is so true. Okay, that's good. Next. So that's one of the things I was looking for, genetics. And then what else? There's one.
Prof, consumption of brucutu bitters.
Look at him. Okay. I think you should put it together and call it diet. Everything put together, call it diet. Anything that goes into your mouth, food, diet. That's what probably you want to say. So alcohol or food intake. Yes, Fanuel.
Yeah, I'm thinking of your mental health.
Mental health. Yes. Okay, so I agree with you, but we put all of that together and called it other diseases. Let's call it other diseases. Mental health, whether it is cancer, diabetes, other health challenges you have will lead to your blood pressure. And it's not only mental health, okay? Diabetes can also bring about hypertension. They are all correlated and all of that. So these are some factors that can affect. Now, whenever you are doing a regression, practical work for your thesis, you should always think about these possible factors. And if these factors are a lot, your R square will come down. Write it down. If these factors are a lot, your R square, if the factors, there are some factors that has to be there, but they have not been included in the model, your R square will be penalized. Okay, let's go to the next one. Last one, quantity demanded. That's a very popular one I've just given you. Quantity demanded of a commodity is a function of the price. Okay, it's a function of the price, the complement price, the income of the people, or whether the good is a normal good or an inferior good, the income, then the price of substitutes, the adverts, the price of complements, and then the population. Is there any other factor which must be in the error term, which can affect the quantity demanded but haven't been included here? Nobody should mention taste and taste and preferences. Which other factor can bring about demand but haven't been captured here? There are quite a number. These are all theories of regression. That's what I'm doing. Let's start. Jessica. Give me another factor. Jessica.
So I think technological changes would
Okay.
affect. Yeah.
Richmond.
Yes, sir. Please, can we add gender?
Gender, no. Oh, by the way, the BP should have added pregnancy. You can also bring about that. Yes, quantity demanded.
Doc.
Yes.
I want to ask a question. Somebody just said gender, and he said no. Like, can you explain why?
Can the person rather explain?
Okay.
So, for me, I think gender can influence quantity demanded in a way, because there are some stuffs that will be like demanded in terms of whether in terms of gender specific.
Yeah, but I didn't bring those particular factors. I didn't also tell you the quantity demanded. What the quantity demanded is.
Oh, okay.
So because then otherwise, then there's going to be several other quantity demanders. So I also didn't tell you the quantity demanded when it leaves that room for any possibility to be used. Okay. So let's say the quantity demanded of shoes. When I say quantity demanded of shoes, I've also not talked about whether women's shoes or men's shoes, for you to not say that, oh, if it is men's shoe, the men will buy it more. If it's women's shoe, I don't want to bring, this specificities for you to, because there are only two genders. So for me to say that gender, but pregnancy like this, men are never going to be pregnant. So that one is obvious. To say that women will have more blood pressure if they are pregnant, because there's no way a man will ever have pregnant. But then for some goods, men are going to be buying it more too. For some goods, women are also going to be buying it more. So for me to accept gender, it's difficult because I've not told you the specific good.
Prof, how about price of related goods?
That is the PS and PC that you see on the screen. The PS is the price of substitute. PC is the price of complement.
Expectation of future price.
Excellent. I love that. That is good one. Expectation of future prices can also affect the demand for the current price. That is good. What else? Theophilus.
Time and season, Prof.
Excellent. Seasonality. Seasonality. You guys are now here. Okay. Weather, seasonality. It can affect that. What else?
Of economic conditions.
That will affect everybody.
It will also affect quantity demand.
It will affect everybody, everything. So it's too broad. When it is too broad like that, it's quite, it's like saying GDP, interest rate, exchange rate, all of these things are macroeconomic factors. It will affect everybody. Do you know location can affect quantity demanded? Location of something. So
yes.
Sometimes depending on the distance and the location of where you are, you might demand something, than another something. Okay, if it is closer to you. Yes, Albert. Albert.
Yes. So please, I wanted to ask, they say demand and supply is correlated. Can supply be a factor?
No.
Oh, okay.
Why? I know what you're saying. Like when the supplier supplies more, then people will demand. It's not true. If you supply more salt, and I don't need salt, people will not demand more salt than what they have demanded.
Doc, does that mean the reverse is true?
The reverse is not true. It's the same thing.
What?
Doc, since you mentioned location, can we also say religious factors?
Of course, you can. So you are doing copy and paste. Yes. Depends on the type of good, though. It depends on the type of good, like the one we have in our example. All right. So at least you get the point. This is just to make you get the point. Okay. We will later talk about how to interpret the coefficient, the numbers. For now, keep this in mind that this is what we mean by the generalized function, regression function. Keep this in mind. This is when you are writing your thesis, your dissertation, your project, your long essay, anything, you will have to specify your model like this. Do the general specification like the one down here, and then do the specific specification up here. Remember, the I means that we are dealing with a cross-sectional data. The data is not panel. When it is panel, you have IT, substrate IT, which means it is changing with time and with individuals. So all that we are having here is just changing with individuals, changing with individuals. So please take note. Take note of that so that you are not confused in any way. What I'm teaching you is not only for exams, I'm teaching you also for your thesis. So please take it. All right. Now, there's something we call Gauss-Markov assumption for OLS. Okay. Gauss-Markov assumption basically talks about factors that must be in place for certain things. Let me tell you something about assumptions. Assumptions simply mean certain things that must be in place for certain things to work. Write it down. Guys, when I'm talking, write it down, because there are some things I've learned for years, they are in my head. And sometimes the simplest way to explain them are what I say, and you won't get that anywhere. Assumptions are certain things that must be in place. The moment you say that the University of Ghana is running, you have already assumed that lecturers are in place, students are in place, the boards are in place, textbooks are there, board is there, the building is there, everything. You made those assumptions already. Now, for regression to work, for ordinary least squares regression to work, okay, certain things must be in place. And when all of these things are properly in place, we have something we call best linear unbiased estimator. Best linear unbiased estimator, that's the blue. The blue is for the beta parameters. These betas, the betas, they are the ones that you expect them to be blue. B-L-U-E, best linear unbiased estimator. Best means it has a minimum variance. Linear means the relationship is linear. Unbiased means that the beta value corresponds or converges towards the true value of beta. And the estimator itself is the beta value without a cap. But once you estimate with a cap, then you now have an estimate. The difference between an estimator and an estimate is that the estimator is the process of estimating the estimate. Okay. Now, so let's look at assumptions. Certain things that must be in place for certain things to work. Guys, check me. I'll give you most of these assumptions. An example for you to explain them to me. So you got to understand them. If you don't understand them here, ask me. Number one, linearity. Linearity. The relationship between X and Y must be linear. It mustn't be quadrilinear. It mustn't be quadrilateral. It mustn't be polynomial. It mustn't be nonlinear. It must be linear. Okay. What do I mean? If X is going up, Y is coming down. S is going up, Y is coming down. S is going up, Y is coming down. That is linear. That is linear. That is linear. X is going up, Y is going up. It's still linear. X is going up, Y is going up. It's still linear. It must follow that. Okay. It must follow that. But where X is going up, Y is going up, but also S is going up, Y is coming down. You know, when it is like that, that is non-linear. We want the relationship to be linear. And most relationships are linear, but some relationships are not linear. For regression to work, you got to check for linearity. Number two, the errors must be normally distributed with a zero mean. Okay, I'll come back to that. The errors must be normally distributed. The expected value of the error term must be zero. The errors are the same as the residuals. They must be stochastic, meaning they must have a zero mean. I've said this thing before, and it's one of them. Number three, the independent variables must not depend on each other. the independent variables must not, okay, no. The observations must not depend on each other. So when you go and take the data for the shop, a particular shop, that particular shop must not have a relationship with another shop. Otherwise, because it has a relationship with another shop, it might look like that other shop's relationship is got with this, is influencing this with that. So let's say that there is some relationship between shop A and shop B. So when there's more demand in shop A, it might be because there is that relationship. So in short, we don't want dependency across the individuals. Number 4, there must be homoscedasticity. In other words, there must be no heteroscedasticity. What does that mean? Homoscedasticity means that there must not be a pattern. Okay, there must not be a pattern in the errors. So when I plot the errors, the residuals, okay, the variances must be constant. The variances has got to be constant. There must not be a pattern that you can detect from that. And mathematically, what it means is that we've already said that the error must not, the expected value of the error must be 0. We've said that here. Okay. So the error must be independently. Now look on the right side here. Okay. The errors must be independently and identically distributed. That's what this mathematics is showing. Oops. The errors here must be independently and identically distributed. Distributed here is this tilde sign, distributed. Okay, normally distributed. That is why you have this N here. The errors, error I, must be independently and identically normally distributed with a 0 mean, which corresponds to the stochastic nature of the residuals, and a constant variance, this one. This is a variance, and the I is an identity matrix, which shows that it has to be constant. In short, most of the assumptions here are about the errors, the residuals, the errors, the residuals, the errors, the residual. You don't want error. First of all, you don't even want them to be there. If they are not there, then we don't have any problem. So there must be homoscedastic. There must not be heteroscedastic. Heteroscedastic is when you have non-constant variance of the residuals. Now, I will hold on to this one. I'll come back to that because I still want to talk about the errors. Another thing about the errors is that 2 errors must not be related with each other. So this is error I and error J. There must be no covariance between them. Covariation means they are related. Covariation means there's correlationship. And what this is saying is that the correlationship between them should be 0. In other words, there must not be correlation between errors, error I and error J, or even error I over time. There mustn't be. So the errors must not be correlated over time. They must not be correlated among other errors. They mustn't also be correlated over time among themselves. So the error associated with shop I or shop number 1 should not be correlated with that same, with an error of shop 1 in another year. It mustn't be correlated. And then the error for shop 1 must also not be correlated with the error for shop 2. That they are separate, I and J, they are separate, but they must still not be related. Not be correlated means they mustn't be related. Not be related means the one should not depend on the other. Read about them if you want to know. Okay. Now let me go back to this. We've spoken about no high multicollinearity. We've said it. That is not about the errors. That is about the predictors or the regressors or the independent variable or the features. These assumptions have to be there for regression to work. Ladies and gentlemen, we are ready now to look at a regression practically. Okay. So let's go back to our analysis, okay, and then look at the first question here. To start our regression, let's remind ourselves about correlation. We've already looked at the correlation, but I just want to pick one and show you how to draw a simple correlation. By the way, a simple regression or a simple correlation can be easily done in Excel. Excel can draw the regression line for you in an XY graph. We call it a Cartesian plane. So we can use a scatter plot. because that would display the relationship between two numeric variables. And in our case, we have two numeric variables, say quantity demanded and price. So here, you can see that I'm showing a quantity demanded in the DF data set. And then I'm showing price in the same DF data set. The quantity demanded should be plotted on the x-axis. Y should be plotted on the y-axis. I'm using a scatter plot matrix in the CBEN library. I want the colors of the plot to be red. I want the edges of the colors to be black. Okay? And I want them positioned in a 60% mark. The S here is indicating the sizing. And then I also want to invoke my NumPy and my pandas. I want to just let you know that these are the data. I'm going to create a new data set for this simple regression. So I create a data frame, and I only want to pick P from the DF data and then Q from the DF data. So I'm creating a new data frame called data from the DF data frame. And I've called it data. I can run this to show the head of the data. Let's see. By the way, let me show you the scatter plot first. There you go. So now you can see that price is on the y-axis, quantity demanded is on the x-axis. This is a relationship between price and quantity. Looking at the scatter plot, is it showing a positive or negative relationship?
Negative.
It's negative because it's downward sloping from left to right. Now you can see that these are the data points, but you should know that the data points were totally 40. But what you are seeing here is not 40. Okay, so I just want you to know that the scatter plot doesn't bring all the things you want to see there. Some are hidden behind others, multiple ways. But this is how it is shown. 40 observations, even though it's not necessarily 40 on the graph. Now, let's now show the head of the new data. I want to show you that first. So you can see that here, I've just plotted the head of the new data. I've created a new data called data for only the price and the quantity. In other words, I've just gone into the original data set and pulled out just the PQ because I want to just deal with two variable case for simple regression. Okay, now that we see the data, let us run the model between these two. Remember, the relationship is negative. The correlation was negative 0.87. So we are going to check the regression coefficient, and we expect it to be negative. If the regression coefficient doesn't show negativity, big problem. So let's run the regression. To do that, we are going to use something called stat models. Okay. That stat model, so we create P. P is our independent variable. We create Q. Q is our dependent variable. Remember, they are all coming from the original data set. Then we create the independent variable and add the constant to it. Okay. So in other words, we are telling the Python package that I want you to create an intercept and add it to the model. This is a model. Okay. It's an OLS model, ordinary least squares model. The dependent variable is the first one to come. That is a Q. The independent variable is the second one to come. That is a P. If there were more independent variables, we would have done that. This fit means that we are estimating a fitted line or regression line. Now, this next command says that it should print the results, the summary of the entire result. But it should also create the residuals. Now look at the residuals. How do you create the residuals? The residuals is the actual Q minus the predicted. You remember I showed it some few minutes ago. How did I show it? I told you that the Y minus the Y cap is equal to minus the Y cap. Oh, why is this not showing? It's equal to, oh, my distance is slowing down. Just so let me give it time. I don't know why. Still not showing it. Anyway. But you get what I mean. Okay. The Y, so in this case, the Q minus the Q cap will be the residuals. So you can see that this residuals has been created down here, residual is Q minus the model that you have estimated, the predicted, residual, and the predicted Q. Okay. So that will create a residual. Then I've indicated that I want you to estimate the mean of the residuals. Remember, we said that the mean of the residual should be 0. So it will calculate it and print it for us to see. And I've written here, you should have the mean of the residual to be 0 here. Let's see that result. Remember, the regression itself will come before the mean of the residuals will come. It's running. You should do the same thing to yours. I mean, you would have created your own data. So this is an entire OLS results here. It has several things, okay? In our next meeting, we shall look at these several things. But it has a lot of things, the dependent variable, the independent variable, everything is here. But more importantly, look at the command I said. We commanded it should give us the mean of the residuals. And we normally say that the mean of the residuals should be what? Should be 0. And this is actually 0. So it means that we have satisfied the regression assumption. Now let's look at the coefficient of the price. You saw that the relationship was negative. The actual value is negative 14.26. So that satisfies the relationship. We wanted a constant. It has given us a constant. Remember, this is a simple regression. We've not included the others. Okay. So this is what you see. I will not talk about this. I will not interpret this because I will do that when we get to the multiple regression, which includes also the price. But for now, let's leave it here. We can plot the entire regression line. You see, what we showed was a scatter plot. This was a scatter plot. And now let's plot the entire regression line. Okay. So we'll create a figure, and we create a figure with 2 columns. So the subplot means we want only 2 columns. The size of the figure should be 14 by 5. This will plot the regression line. It is having a color of blue. Using the actual data, all of these things are self-explanatory. Independent variables is there, residual plot. I also want to plot the residuals. And then you see that the residual is actually 0. You're going to see the mean of the residuals. So let's plot this and show the results. There you go. So now look at a beautiful regression line here. I've given this title. That's why the title is shown. The dependent variable is on the y-axis, is Q. That is showing there. The independent variable is on the x-axis, is P, showing there. The regression is actually downward sloping, just as we thought. The actual data, the regression equation is also here. Now watch this. I wrote that equation in the graph here. Where is that? So when you look at the graph, I've indicated that you should write the regression equation there. Okay. So because I've indicated that you should write the regression equation there, the equation will come along with that. And so that is why you see the actual data point are there. The regression line is there because I've indicated that. Now look at the residuals. The 0 is the horizontal line, the red horizontal line. That is a 0 mark. And you can see that the 0 residual line is showing. Okay, so the 0 residual line is a clear indication that the residuals are approximately 0. Otherwise, this line would have gone up somewhere, down somewhere. Okay, but it's straight on the 0, which means that the errors are 0. So this is just a picturesque understanding of the entire regression. If I show you a simple regression like this and I tell you to interpret it specifically, and write the equations and all of that, you should be able to do. Okay. Now let's go to the multiple regression. We will not finish the multiple regression today. We will not finish it today, but I just want to give you that. So the first thing we are going to do is to run the OLS regression on the gene. But here is something. I'm not going to use Python code. I'm going to use R code, but in Python. This is a very, very unique thing to do because R was used in statistics long before Python was popular. I love using R software. But Python is something you guys have started, so I decided to follow suit. But R gives you some beautiful things, a beautiful understanding of things than Python would do. You see, for Python, you need to convert all the dummies to numbers before you can estimate. But you don't have to do that in R. R, you tell it will do it all by itself. It's a highly AI-driven mechanism. So what I have done here is that I want to use R for it. Some of the data science libraries for Python, they copy the way R behaves. Okay? And this makes it very easy to transform from R to Python, but not the other way around. So in R, instead of defining separate Y, let me just go here. Instead of defining separate Y matrices, okay. In other words, instead of creating dummies, like Python would do, you have to create the dummies. You can simply pass the R formula from this equation. Let's say the function of Y as a function of X. You can just pass this formula. And by the way, I wrote these things mathematically using LaTeX inside a Python. So you can enjoy using it. For example, when I double click, you see that anytime you want to write the LaTeX, you need to bring a dollar symbol in front and behind it. And then you can write it. Then when you run it, you can look beautifully like a mathematical equation. Anyway, so this function will take care of the rest. And the stats model that we activated for the linear model, the stat model will include a whole library for doing things in our way. But you have to import the stat model formula API, this one. You have to import it. And I've already done the import here. That is why we're able to, I've done the import here, statmodel.api assignment. So it's already been imported. I have to import that in addition to the API library. And also in the formula API, you use lowercase OLS. Okay, this one you can always change, but I've decided to use lowercase OLS. So we are going to edit this model. So here you have the importation. And now I'm going to create a formula for the multiple regression. So how do you do that? I am going to estimate the multiple regression. I've left this thing for you to do it also yourself so that you can follow me in the way I am doing it so that you can follow the same thing. So let's do that together. So you write gen equals to SNF, okay, OLS. Then you bring a bracket. So I'm going to remove everything here. OLS, bring a bracket, write the dependent variable. What is a dependent variable? You have to bring apostrophe first. The dependent variable, then you write your tilde sign. Okay, so this is a Greek letter, tilde. Then you write the independent variables. The first is P plus C is price, complement price, plus income, M, plus the dummies. The dummies were LOC, which is for location. So you do that, plus occupation, OCC, plus religion, REL. So these are the independent variables. After that, you have to put that in apostrophe as well. Okay, so all of them in apostrophe. Then you do a comma, and then you write the name of the data set. So the write data, the name of the data set is DF. So you write DF there. And then you close the bracket. Okay. Once you're done with that, let's look at the model now. So this is like the model. Now we're going to fit the model. So let's use generate underscore result, RES, equal to. So we are going to generate the results, and then we'll do equal to. Then we type the name of this data, which is gen, the model. So you type gen dot fit. Then you bring a bracket. That's it. So this is going to run the model, but we want to see the results. So let's do another command to bring the result. To get the results, you can just copy this one and do summary. Copy this, paste it, and then do dot summary to bracket, close bracket. Check spellings. Very good. So I'm going to run this, and the entire multiple regression model is going to pop. I hope you are following me. Once you do that, boom, there you go. Everything. The date is there. The time is there. The date is there. The time is there. It's an OLS model. And there are so many things. Look at it. Okay, the P is here, the C is here, the M is here. The reason why I like using this, they have created it for this purpose, is because it picks the independent variables, the dummy ones, and then chooses a level automatically. Okay, it chooses a level. So occupation, there are 3 levels. We have teaching, trading, and fishing. But fishing was not brought because it is a dummy variable, but it's created a coefficient for each level except the reference category. Keep that in mind. There is always a reference category for independent dummies. There's always a reference category. So you can see that it's here. And then you have for religion, you have Christian, Muslim. So which one is a reference category for religion? Which one? Which one is a reference category for religion? Are you guys there?
Buddhist.
Buddhist. Okay. So you see this entire, I'm going to give you an assignment that you will do, and you will go through all of these things. So it's important that when you don't understand something else. Anyway, so all of these results are there. We are going to take each one of these to explain them. Okay, to explain each one of them, because doing the model is beautiful. Everything here is important, guys. Remember, the number of observation was 40 is here. The degrees of freedom, the residuals is 31. The models have got 8 independent variables. They are all here. Okay. We will talk about all the fitness, the things that you can use to determine the reliability of the model. The R squared, adjusted R squared, the Akake information, the Bayesian created. But all of these things, you use them. Okay? We'll discuss them all. The coefficients are the first one. Remember that the coefficient divided by the standard errors will give you the p-value. If you know, you know. This coefficient column divided by this standard error column should give you the t statistic here. If you like, check it. Okay. And then once you get a t statistic, you can read it from the t table, and then you get a probability, the p-value. So this is a p-value, which is coming from having read this. Okay. And then these are the confidence interval, which is the 95% confidence interval. So we will look at the interpretation, but for now, let's look at a very simple one here. If there are some couple of few errors, it will tell you, it says the conditions number is large. This might indicate that there are strong multicollinearity or numerical problems. Now, we can check it to see. Okay. We can check by looking at variance inflation factor to see whether there's a problem with multico. Okay, we shall do that next time. But for now, I'm interested in the first important question here, because I've asked this question both in the assignment and in exam. The question says, specify the whole regression model. Specify the whole regression model based on your output using the same labels as Python produced. Guys, this is important. It's important. Remember some few minutes ago, we were talking about specifying a regression model. In our own, you got to use the same name that was used. The same name. So what do you think will be the first name you will bring? Remember, it is the independent variable. Sorry, the first is the dependent variable. So what is it, do you think is the first you will bring? Let me see. The first you bring. David Bedu. I'm going to put it here. So David Bedu.
Thanks, sir.
Go ahead, I'm listening. David Bedu.
I'm sorry, sir.
Sorry? I can't hear you. What did you say? So the first thing you got to do is to write your dollar symbol. Okay. You're going to write it as a proper mathematical equation.
So the prof is the Q, the quantity.
So you write it. Now, if you want the thing to be in the center, you can double the dollar symbol, like double like this. And then you use a curly bracket, and inside a curly bracket, this one at the back, put this one in front. Inside the curly bracket, you are going to write Q. And then you bring underscore, because the Q is an individual variable. Okay. So you do underscore, then you bring curly bracket again and write I. So it's underscore I. Now we are going to put in the rest of the information. So what's the first thing? After you've written the dependent variable, you write the equal to, then we are going to write the first independent variable. Also, we are going to put that one inside. Okay. Now, I'm going to copy this very one here for Q, and then drop it here for the first independent variable. But it's not Q, so it's supposed to be beta. To do that, you do the backslash and type beta. Backslash and type beta. Then in the bracket, remember it's beta not, so you type 0. Now, in case you don't understand what I've just done, let's run this and see. So you can see that you are getting this equation already. Okay, that's the first thing you're going to do. Then you have to now do plus. And then we write the beta one. So once again, you're going to pick on this very first one. So I'm going to copy this here, paste it there. And then after pasting it, remember, we have to change the beta to beta 1. So this beta is 0, so I change it to 1. But then I need to bring my price, because it's a P that I need to do. So you step out of this. Let me see. Now sometimes the brackets can be so plenty. You even not remember. Okay, so for price, I'm going to just copy this whole thing here again. And remember, I'm doing for price. And then do P and then I. In order to see what is happening, just run it and you can see exactly. And I have my beta 1 price. Price PI is a subscript. Remember, price was used up here. P was used. So I'm going to do that for P. I'm going to do for C. I'm going to do for M. So at this stage, you can just copy. I'm just going to copy everything here together with even the plus. Paste it here and edit it for M. So this was beta 1. Now this is supposed to be beta 2. So change this to 2. This is supposed to be C. Change it to C. And that's it. Leave a space and paste the next one. This is supposed to be beta 3. And then you have M. Occasionally, just double check to be sure that you're on the right track. Bracket is becoming a lot. Let me see. Oh, good. You're on track. So you can see that you have the M. Double click. Bracket is getting plenty in my ears. 1, 2, 1, 2. Why is this thing looking plenty? Okay, so next time I need to just move this one here. And then paste this. And then you do for the next one, which is beta 4. And watch this one, beta 4. And the next variable is location. And watch how it is. This is where you got to be careful. You just have to copy exactly what is here, exactly as it is in the Python result. Don't change it. And then come down here. If you change it, everything is wrong. And replace that whole thing with this value here. Okay, so that is log T urban, whatever it is. You put it here exactly as it is. Now, let's copy another one for beta. That was beta what? That was beta 4. So you do the same thing for beta 5. Okay. So you change this to beta 5. And then you go and pick the next variable. And what is that? That is awk teaching. Just copy it exactly as it is. Don't change anything. Awk teaching. I just hope that you are following. So you do awk teaching. Let's paste that. Now let's show the results. Oh, there's a problem. Of course, when there's a problem with the way you've written the thing, it will exhibit it there. There's a typo somewhere. Okay, so I don't need these brackets. Let's see. Still. So you have beta, you have, what is that? You have beta 3 M. Then you have that of log urban. And then you have beta 4, 5. Of teaching. Everything looks okay to me.
Doc, please,
Yeah.
there should be a curly bracket at the end of beta 2, beta 3.
Beta 2, beta 3. Are you sure?
Yes, Doc.
Where is that? Here?
A curly bracket at the end of beta 2. There should be a last curly bracket.
At the end of beta 2.
After the C_I.
Here?
Yes, there should be a curly bracket there.
Oh, okay. You're right. Let me see, it's true.
Then M_I
Yeah.
to another one. Yes.
And then here too.
Yes.
And then here too.
Then you can take the last two off.
Yeah. Very good. Very good. All right. So you guys can then follow. Okay. What I want to do is I want to just show it all. So I'm just going to copy this and then show it all. I've just added all of the rest and run it here. So now you can see the entire result. This is what we mean by a specified regression model. If you look at some journals, okay, these are some of the things sometimes you might see them do. But that is exactly what it is. You don't change it. Remember to bring your error term here. Oh, and remember the error term is here. It is plus Note the way it looks like. It's epsilon. Okay, there's a backslash epsilon before the underscore I. So it is epsilon. Take note of that. And that gives you this. I have, center aligned them with a double $sign. So that's exactly how you got to write your equation. And now the next part of the question is to write the estimated regression equation. Sorry, that was the specification of the model. So this is the next part, which is regression equation. And you are supposed to convert it to 2 decimal places. So it's just the same thing as this. Okay, I can copy the whole of this and then dump it here. Just dump it here. The only thing you're going to do is that you're going to change the betas to numbers. Okay, so as an example, when you go here, the intercept is 280.27. So you take 280.27. I just want to do the intercept for it. And then when you come here, just change this 280.27. Just that. The whole of this must be changed. And you get 280.27. Correct it to the decimal place. Let's run that and you see the number is showing. Now let's go to the second one for P. P is only the beta you are changing. Let's go and check the P. Remember, the P is negative 3.15. Correct it to the decimal place, don't forget. It's negative. So you copy that whole thing, you come here, and then you changed it up to that. Okay. And then you put that value there. It's negative. So you have to remove this positive. Okay. You have to remove the positive. And now that gives you this answer. Let's run that and you see. So you see that it is negative 3.15. And then you do for the C. And then on and on and on and on and on. Okay. You can do for each one of them. And in fact, I've done for each one of them. So what I'm going to do is that I'm just going to paste it here. So you do for all of them, you change for every one of them. And this gives you the equation of the regression. This time, each with the numbers. Let's run this. And you see that you have the numbers here. And for this, you also have the numbers here. In your assignment, you'll be doing this. And in your exams too, you'll be doing this. In the case of the exam, you got to write it. Got to look at it and write it. So this is how, and watch it, I've put the caps on them. I've put the caps. In case you want to see how the caps is, I wrote /hat before I do the thing, /hat. That's for each one, I write /hat, okay, to put the caps on each one of them, meaning that they've been estimated. They have been estimated. And also note the last one. The last one, there is no error term. Unlike the regression model. In the regression model, there's an error term. But the whole idea is that once you've estimated the model, the error term would have whittled down to 0. So there's no need to deal with the error term. Okay, so we're going to stop here. And then in our last meeting, we are going to continue to wrap up the whole show by looking at the interpretation of the results. Excellent. Any questions, ladies and gentlemen? That brings us to the end of the entire caboodle. If you have a question.
No, please. We have 7 p.m. Supervise.
So I want to welcome all of you to stock price prediction. In your thesis, I know you're all writing your thesis. Each one of you should tell me what topic you're doing for your thesis. Starting with you, Linda, what's the topic?
I'm working on cybersecurity threat in digital transformation, focusing on risk mitigation strategies for businesses.
What about Seth? Richmond.
Hello, sir.
Go ahead. Don't hello, Seth. Just go ahead.
Yes, sir, please. I'm working on predicting stock prices on the Ghana Stock Exchange, a machine learning approach with macroeconomic factors.
It's okay, Kofi.
Please, I am working on public debt. I'm working on the analysis of Ghana's public debt and its influence on economic growth.
Okay, Joseph.
Doc, I'm working on enhancing fixed asset management in the telecommunication industry.
Sharabna.
Data accessibility and security in SMEs.
All right. Some of you will be using some of the models we are going to talk. So work along with me on this. One of the important things you should notice is that you can create table of contents in this. So when you know how to create table of contents, it can help you to be able to get some very nice work analysis. So this is a stock price prediction. We want to predict the price of stock. If you can remember your first assignment I've given you, there are some stock price predictions you are doing. You're calculating Sharpe ratios, you're calculating volatilities, you're calculating other things. This one goes slightly beyond because of the nature of the work. So we are going to look at various supervised learning models. Everything is supervised learning models. Now, it doesn't mean that you wouldn't need unsupervised, because there are some situations you would need unsupervised. Like you could have done classifications before you actually do this. We are going to predict the stock price of Microsoft, okay, using correlated assets. So Microsoft has got its asset, and the asset of Microsoft is usually correlated with that of other companies' assets, or the asset of other companies. So we are going to look at those correlated assets. Because they are correlated, they are like substitutes. Because they are correlated with that of Microsoft, you're going to see how you can use those correlated assets to predict the stock price of Microsoft. But also, we're going to use Microsoft's own historical data. So the data we have is a time series analysis, which means that you have data based on time. Besides, if you want to predict future stock price correctly, then we have to discuss the machine learning framework for general asset class price prediction in finance. And that's what we're going to do. So we're going to discuss several machine learning models, several concepts, also including those in time series. And we shall focus on visualizations, model tuning, and all of that. So let's get the ball rolling. First thing is to tell your problem, define the problem, and then address the problem. Now, in your research, you're supposed to have gaps, okay, research gaps. And let me tell you one of the easy gaps you can identify, given what we are going to do. Existing studies have examined stock price prediction using, classical machine learning models without comparing those models with several other models to see which one is the best. This study makes a contribution in the literature by examining about 14 to 20 different machine learning models and comparing the performance of each of these models on an internationally recognized data set. So that is how you can identify some gaps in the work. Another thing is that the focus is to use Microsoft stock, which is very, very well-known, popular company. The interesting thing is that unlike previous studies that sometimes do not include the historical asset prices of the asset itself, this will look at historical asset price, not just correlated assets, but also historical assets. That is that company's own asset in the past, and how it is performing in the past. All right. Ideally, we should have used weekly return, but we are going to deal with daily return. So I must make that point explicit, even though I've written weekly return. That is going to be our predicted variable. We are going to understand what affects Microsoft stock price. Okay. What affects the stock price? Okay. What makes it go up? What makes it come down? And then we shall include as much information into the model. Okay. You want to note that if the assets are positively correlated with that of Microsoft, it means that when an asset price rises, in this case, when Microsoft asset price rises, or when those asset prices rise, that of Microsoft price will rise in conjunction with them because they are complements in this case. A complement is a product that moves in conjunction with another product. So when they move in conjunction with another product, when that product price rises, in this case, price is like the gain. When it rises, that of Microsoft's own will also rise. So keep that in mind. That is but when they are substitutes, it means that when that of the other prices, they are still correlated, but they are negatively correlated. So when the prices rise, because they are negatively correlated with that of Microsoft prices might fall. We're going to check all of this. The data is from Yahoo Finance. Okay. They've got some very friendly names. You're going to see that. The independent variables that are used are potentially correlated assets. And here they are. The first are the equities or the stocks. So we are going to take, first of all, Microsoft itself is going to be the main thing and other parts of it. We are also going to take Alphabet, which is the parent company for Google. That is another stock price. We are going to take International Business Machine, which is another stock. Now, most of these particular variables, these stock prices, or these three variables, they have moderate positive correlation with each other. In other words, the correlation is between 30% and 50%. So, but we are including these variables. Another variable we are going to be using are the indices. Indices. What are those indices? S&P 500 index. We're going to use that. Okay. The name they normally give to it is the GSPC. Then the Dow Jones index. The name they normally give to it is the DJI. Then the volatility index, VIX. Okay. Now, when you go to Yahoo, the data set, they are called tickers. So the tickers for S&P 500 is GSCP. And it is the S&P 500. I've indicated here that it is often used in Yahoo Finance and other platforms. So that is the name. Now, do you all know the S&P 500? Do you all know what the S&P 500 is? Richmond, who is doing stock price? If you are doing stock price, you should be able to tell me. The guy, is it Isaac? Do you know the S&P 500?
It's me.
Tell me.
Yes, sir. Yes, sir.
So I also know the S&P 500.
Go ahead and tell me what it is.
So there are 500 stocks in the US that are currently being tracked, and it gives an indication of the movement of the market in the US. Top 500 companies on the US stocks exchange.
You see, at first you didn't say top 500 companies. So now you are qualifying it, which is what I wanted. Okay, so those are the S&P 500. Very, very respectable companies. If you are trading there, so they themselves have created a whole index for themselves. Okay, so the next one is the Dow Jones Industrial Average, DJIA. And when you look at it, its tickers, that is the name they use in the Yahoo Finance, is DJI. It is the important US stock market index. That is also another index that we are going to check its relationship with the Microsoft stock price. Then we have the volatility index, which measures the stock market's expectation of volatility based on the S&P 500 index options. Sometimes it's called the fear fudge, you know, because it will determine whether you'll be afraid to go into the S&P 500 or not. Now, note that the S&P 500 and the Dow Jones, they are highly positively correlated, the two of them. The correlation between them is 90% to 99%. Okay. The S&P and then the volatility index, they also have some strong correlation, but they are in the negative section. So negative 70% and 90%. So those are just to give you, you see your variables. The last time I was telling you, you have to know everything about the variables you are using for your research. When somebody asks you what are they, don't say my data, I have my data. They use the word data, without knowing exactly what data. And when you get to know the data, what variable? What is the variable measured in? Is it measured in percentage? Is it measured in kilograms? Is it measured in million per square meter? Understand each column, each variable very, very well, in total. All right, let's move on. The other groups of variables are the currency pairs. So we are looking at currency pairs from the stock market, the Forex market. The first are the JPY and X, that is the Japanese yen and that of the US dollars. And then the other one is the British pound and that of the US dollars. Just writing them like this is not enough, but actually telling the reader that the correlation between these variables, these two variables, are 50 to 70% negative. Okay? Which means that if the US dollar should go up, or if the exchange rate between the US dollar go up, that of the British pound and the US would also go down, you know, in terms of, not will also go down, it goes down in proportion to, they are associated by 50 to 70% in negative terms. So the correlation is moderate to strong negative. So if the US strengthens across the board, okay, like the dollar is strengthening across the board, then the US Japanese currency will rise. And then that of the British pound and the dollar will fall. So that shows that there's a negative relationship between the US yen or the dollar yen rate versus the pound dollar rate. And that is a typical example of this. But these ones are all related, somehow associated with what? With Microsoft, you know, stock price. That is what we are going to look at. I've indicated here that the equity market have trading holidays. In case you don't know, well, most of you know this. Okay. The currency market, the equity market are those ones up here, okay, the stock market. But in the currency market or the Forex market, they don't have stock trading holidays. That is running every time. That's why it is very, very volatile. Okay. So the alignment of the date that you're going to see in the data set across all the time period is ensured before any modeling analysis will be done. If you want to find the data, it is here. Well, the original data was here, but now I had to get it from a different place. So we're going to use the daily closing price of the last 10 years from 2010 onwards. That's what we're going to use. The closing price for the Microsoft. In short, these are daily stock prices. That's all. The stock prices are daily. So it's not monthly, it's not weekly, it's daily. The goal of the study is to predict stock price correctly. Using what we have, we're going to predict the stock price of Microsoft. and show the infrastructure and framework for each step of time series, each step of supervised regression models for modeling stock price prediction. If you have a question at any point, you always have to ask. Okay. Now, how do you get the data? Yeah.
Doc, please, can we get a file, the notebook file?
I think Linda will answer you that question. Okay, so the data set. Linda, answer him.
Sorry, my network. It's on the page. Set. I've sent it to you.
I see, it just goes to tell me the serious people on the page. That's what it means. If people are not serious, it becomes so evident in situations like this. It means they ignore whatever you send them. Okay. So we're going to load the Python packages. But you see, before you start something, you got to know your Python package before you load them. So you got to get all your Python packages or your libraries that you are going to use. Get them all ready. So here, you're going to load packages for data preparation, data manipulation, model evaluation, model tuning, all of that. You're going to load them here. So here you go. You have everything here. It's quite a lot of data. But again, they are not that lost. We all know about NumPy. You know, this is a whole thesis you get together. NumPy, pandas, okay? And this Panda data reader is good because ideally, originally, I wanted to load the data, run this thing and make sure there's no mistake. If there's a mistake, let me know. So sometimes when you have to read the data from another website, this will do that for you. As for matplotlib, like pyplot, we know it. Pandas plotting, import scatterplot matrix, because we shall do scatterplot matrix. We do that. Seaborn, you know it. Scikit-learn, you know it. It's for pre-processing. And then in case you want to change the scale or standardize the scale, because the data might not be in a similar scale, we want to standardize. We shall use this scikit-learn train test split for the training and the splitting of the data. You see that. We shall use this one for k-fold cross-validation. This is very, very useful to evaluate the technique. So whatever technique you're using, you're going to check whether it is true, which technique is better. Okay. And I've indicated here that instead of just splitting the data into the sample, train, and test, which is the 80-20%, what the k-fold does is to do multiple splitting 10 times. So sometimes the k becomes 10, and you will learn very soon why it is 10. So we use that k-fold split to do multiple splitting of the data set, and then use it to check. And then you have the cross-validating score. The score you will get from the k-fold and other approaches, it will give you which data is good, or which model, which machine learning algorithm is good to use. The gray search is used in conjunction with the cross-validation to automatically test different combination of hyperparameters if we have to do that. So we load that as well. And then we load all the algorithms, the packages. Linear regression, we shall run it. Lasso regression, we shall run it. I don't know, I didn't bring ridge regression, but you can also do ridge regression. In fact, let me see if I can run ridge regression. Let me just check whether ridge. Okay, so you have that, you have decision tree, k-neighbor, support vector regression, random forest, gradient boosting. Okay. We shall look at these two. We shall have the other boost. Okay, the MLP regressor, the Keras classifier will be used to do the wrappings Then those for the deep learning, which will be for tomorrow, we shall look at the long short-term memory, the SGD, the dense and sequential. All of these are for. Okay. I've already mentioned the ARIMA models. All of that are for this. And then in case you have to save some things, dump some things, you can have that. Okay. That is a ARIMA. You use this for the ARIMA model. We shall look at autoregressive integrated moving average. And then feature selection is easy. There's no need for feature selection because I've done an easy way where we don't need feature selection for this because the features are few anyway. So all of these are there. We are going to run this. When you have a challenge, it means that you have to install some packages before you run them. So let's do that and see. I just did that and it's loaded perfectly in my side. So even though I just included a range, the range is included. So can you run yours and confirm if yours is also sorted? Who has run it?
Doc, I have, I'm getting an error. They said no model name Panda Reader.
It says what?
No model named Pandas Reader, Data Reader.
All right. Okay, so you can remove this one and run it again.
Okay.
Just highlight and remove so that in case you have to bring it back, you know. Who raised a hand?
Please, it's me. I'm facing the same challenge, so I'll do as you are saying.
All right. So do that and let's quickly know. You got to be moving along with me because what we are going to do is very important. If you don't see the results, you wouldn't know what to do. And you'll be doing these things.
I've been able to run mine.
Good. Who else has been able to run? Those of you who removed the Panda Reader, is this still running?
No, sir. Another error on my end.
The same.
Mention the error. But when it's another error and you've not mentioned the error, it's like you're telling
I was now scrolling down. They said no model name.
Talk. Everybody.
Mine is no model named. Is it Ski Kiras or something like that?
Samuel, I've shared this thing on your page. You two don't follow my messages. It's really, really bad when I sent in. I posted all of this into your pages and you don't even follow. Now, is it a Kiras wrapper? Is it a Kiras wrapper you are talking about?
Yes, please.
Okay, so you see down here, you have Kiras wrapper here. I don't know which of the Kiras wrappers you're telling, but if it is that, if it is a Kiras wrapper, you can do pip install Kiras. This one. Pip install Kiras. The pip, before the pip, you have to bring the exclamation mark. You have to do it on top of this, at the top here. So you can create a cell, click here, enter to create an empty cell, and just do this, and then do pip, and then you can pip install this Kiras wrapper, or this Kiras. And then after that, you run the command, the code. You have to be updating me so that I don't move fast because I'm going to move until you tell me. I just don't want to reach to a certain level. Then you now say that I still don't have it.
Please, I've done it, but then it's still running.
Okay. If your internet is also not good, you cannot. All right. Who has been able to do it? Let me see which people have been able to do. Who has been able to do without any challenge? So take note, all of these are the variables that we have. And then you have MSVT. All of these are the lagged, it's the same as the original daily returns, but just that. So if you check the original daily returns, Microsoft _DT, this is the same thing there. Okay. So when you check the data, you see that it is repeated. It's the same thing. So it's like what you're saying is that the variable is dependent on itself. The stock is, because if it is dependent on previous stocks, it can also depend on its current stock, because the current stock price can determine the returns of that same stock. Then you have the 3-day cumulative return that can also affect this variable. Then you have 6-day cumulative return that can also affect the current variable, and then 12-day cumulative return. So all of these are Microsoft's own past and present variables. I've explained it here. It's just to give you a more detailed information about the data set. So I've explained it here that the dependent variable or the predicted variable is the next day's Microsoft stock. Yes, set.
Yeah, so I just wanted to get some understanding, please. So the 3-day, 6-day, and then the D1, and then is it the same as that? Is it the explanation of the term lag features?
Yes.
Okay, sir.
Yes.
Thank you.
Now, for the independent variables, I've already indicated that we are using those correlated assets, okay, which we have spoken about. IBM and Google, they are assets. Currencies, we've already mentioned them. Japanese dollar, British pound dollar. And then we also have the indices alongside the Microsoft specific features here. Now, you will notice that I'll put a sentence here that the rest of the features were dropped. Which were dropped? The very Microsoft specific features, some of them were dropped, because when I got the data from Yahoo Finance, I saw that 2 of the variables are useless. So I had to drop them. And I've indicated here that they've been dropped. So what you are going to load now, you will not see the dropped data, but I've dropped 2 of them because they're not important. So I sent you the Excel file here, didn't I? So load this data set. It will load the data and automatically show the head of the data. Let's do that. So that is the loaded data, and that is also the head of the data. Do that, and you should have this. Now, this command here, what is done is that it drops all variables that have NA. So when the variable has NA, it will drop that particular, column or row. So that is why you can see that the first one is number 3. But ideally, it's supposed to be 0, 1, 2, 3, 4, 5. Okay, so the next one, you have 8. Why? Because I have dropped this command, drop NA, actually drops some of the variables that are there. I hope you understand. And this shows the first 4 parts of the data. If you want to show just the two rows, okay, that's it. You just have the 2 rows. I just changed this value to 2, and you can just look at the 2 rows. Now look at the columns. You can see that the dependent variable is rather here.
Sorry, Doc. Please, the data, I don't see it in the chat. Could you please reshare it, or could someone please reshare it?
Do you all don't have it?
Yes, Doc. I don't have it too.
No, please.
We don't have it there.
So you run the thing, and then you realize you don't have it.
No, sir, we don't have this data.
But ideally, you should have it before you run. Okay. Can somebody just say hi on the page? Just say hi on the page so that I can send it there. You should have, anyway, opened it. All right, so you should all check and then you'll see there. So because the command is there, remember to place the data in your working directory. Why is this thing showing that?
Okay, I'm all good.
You have your data set.
Yes, I've also loaded my data.
So you'll notice that the first data set is 7th January 2010. Now, if you could remember, we indicated that the data is from 1st January 2010. But because you have cleared some variables and all that, now it starts from 7th January 2010. And then the next command at the bottom here will also show you the tail of the data. So even after removing some rows, you will notice that we have, well, the data is still showing 3,999 observations. Of course, some of them are empty. So it is when you look at the information, data information, we'll get to the exact number of observations. But every column here should be something you should now be familiar with. I was talking about this data that it has repeated itself. So look at it. So if you look at this very one here, MSFT underscore DT is the same thing here. Okay, the second value is also the same thing there. So that is what we mean by the fact that it is a current MSPT and then also its self. Okay, so it's like that variable has been duplicated by itself. All right. So now that we have the data well loaded, we are ready to do some analysis. The first thing we want to do is to check if the dependent variable is normally distributed. So this is a dependent variable, MSFT underscore predict. This is the Microsoft stock price. And we want to know if this variable is normal. So we need to check for normality. We import SciPy, okay? And then we test for the statistic using the Shapiro test. Okay? And the Shapiro test is in such a way that when you get a test, the null is saying that the data is normally distributed. The alternative is saying that the data is not normally distributed. Now we want a data that is normal. So the ranges are 0. The test statistic ranges between 0 and 1. If the test statistic is closer to 1, the data is more normal. If the p-value is less than 5%, we retain normality. Sorry, we reject normality. But if the p-value is rather bigger, we fail to reject normality. This is very important. So we want the p-value to be big for us to conclude that the data is likely normal. Well, when you run this command, you get this result. Okay, so we've been able to see that the data is not normally distributed. So that is it. The data is not normally distributed. Strangely though, maybe because it's quite a lot, I decided to still run the kernel density plot for the data. So this, you can do this along with me. When you run the kernel density plot with the data, it appears the data is normally distributed. But if you look at the edge, at the end, they are not that smooth. They are not that smooth. So probably that non-smoothness shows why it's not normally distributed, because the Shapiro test clearly showed that it's not normally distributed. Guys, when you are doing stock price data and the data is not normal, don't go ahead and use it. Don't do that. Okay. By the way, you can do this through to fill in the space so that you will notice that now we've filled the space and you still notice that the data is not normally distributed. At the top, it might look like it's normal, but at the tails, it's not normal at all. So what do you do? Well, there's another graph you can do to check for normality. This graph shows both the kernel density as well as a histogram. Yes, Seth.
Yeah, sorry. After I loaded my file, when I do the df.head, I'm getting an empty rows. No data was being loaded. I don't know if anybody was able to get data. If I don't, or it's only me.
Did you place this thing inside your working directory?
Yes, sir. It's there. It's able to read it. It doesn't say not file not found. Okay, so okay. So after I run it, I get empty. It just prints the headers, and it's saying I don't have data. Meanwhile,
open the Excel and see.
Yeah, it has, like, I can see the CSV file here. But I don't know if anybody, and apart from, I don't know if any of the team members have been able to.
Yeah, they've all said they've done it.
Oh.
Yeah, everything is good at my end.
Run it again and let's see.
I can even start by running the first. I've run this, then I come and run.
But yeah, but I told you not to run that. Do you remember?
This one.
No, the second one. I said it here, and you shouldn't
This
run
one.
that. In fact, remove that command.
So I should only run this part. Or say, can you help me?
No, I said you should remove that command. Delete that command where you are now.
Here.
Yeah, delete that cell, that entire cell.
Okay, sir. Okay, sir. I'm coming to do that, sir.
You find it difficult to do that?
No, I just wanted to copy it. Okay, so I've deleted it.
Now start again. Start running everything again. Okay.
Okay, so I don't want to delay the class. We can continue. So
But I told you to also hash the data reader.
I thought it was because they were having errors. That's why I was able to install it.
Okay. What was the second command? Go up. Let me see that second. What was it? No. After this, what was the next? Okay, so you didn't do any pip install.
I did them. I've run them already, sir.
Okay. So what could be the reason why your data heading is not showing? I mean, just your data heading is showing. Wait, give it time. Sometimes you may have to restart.
Yes, sir. Okay, sir. We can continue. I'll come back to you.
You can restart the kernel rather, but
okay, sir.
Moving on. All right, so showing the data, after showing the histogram, which of course depicts the same thing as the before, we are now ready to do the exploratory data analysis. Now watch it carefully. You see that normally people will show the data if they want to do. I've shown that in order to describe the data, I am rounding the data to 3 decimal places here. And I'm transposing. In fact, you can sometimes use just the letter T, but I've written transpose. So you can transpose the data so that they will rather show vertical instead of showing horizontal. Okay, so let's do that. You can run this command and it will show the data set, as you can see here. It will show the data set for each variable. You'll be able to see the mean, the standard deviation, the minimum, and all the percentiles, as well as the maximum. Check carefully, and you see that the mean of most of the data are almost 0. Okay, the mean of most of the data are almost 0. Remember, these are stock prices, and you can have even negatives, okay, of stock prices. The stock can go down today, rise up tomorrow. Very volatile market that we have. So this is how your descriptives look like. Now, what can you say about descriptives? One of the first quick things you can notice about descriptives is that if the standard deviation is bigger than the mean, it shows high variability. That's it. So check for the MSFDT here. The standard deviation is bigger than the mean. So that means that there's a lot of variability in the data set. That's all. Now, if you check for the others, it appears that they are all like that. Okay? For most cases, the standard deviation is bigger than the mean. For all cases, actually. For all. The standard deviation is bigger than the mean. So there's a lot of variability. What does that mean? It means that these are daily returns. And that means that every day, you can have a boom variable and a ting variable. So the gaps, the variances are very wide. The variances are very wide for all variables. And that is depicted by a standard deviation being bigger than the mean. I'm saying some of these things because when I give you the project, you would have to comment on some of these things. And so that's why I'm giving it. And if you're writing your thesis too, that's the same thing you'll be doing in the process. Okay. The next thing is to visualize some stocks. So I put a statement here that the fastest way to learn about the data is to visualize it, which means that you have to independently understand each attribute of the data. Now we will look at the two things, the scatter plot matrix and then the correlation matrix. We are going to look at both. These plots will give us a sense of the interdependence of the data. Both of them are correlation. Correlations can be calculated and displayed for each pair of the variables by creating a correlation matrix. Okay. Beside the relationship between the independent variables and the dependent variable, it can also give you a relationship between independent variables so that in case there is multicollinearity or some variables are multicollinear, it can depict that. Very useful because in some machine learning algorithms like linear programming, so like linear regression and logistic regression, you can have a very poor performance if they are highly multicollinear variables. That statement I put, the highly correlated input variables, they're the same as highly multicollinear variables. So let's look at the distribution of the entire data for each stock. So this is the distribution for each of the stock. We looked at it earlier. Okay. So this plot is the distribution. Now look at it carefully. There's something I'm going to ask. If you check carefully, they all seems to be similar. Okay, but let's focus on some particular variables, our predicted variable, our target variable, MSFT pred. If you check it, we've already confirmed that it's not normal, by the way. So don't worry about that. Okay, now I'm going to draw the kernel density plot, which is similar to the distribution of this. Again, check it carefully. They are all looking similar. That similarity there. Oh, by the way, you should run these two results, you get the answers. So this one is a histogram. Okay. Run this. It takes some bit of time though. Okay, now you have the result. Then the kernel density plot. It shows some bit of. Okay. Now you can see that there are variances a lot, but check this one. Whilst all the kernel density plots look very, very tiny, look at the volatility, index here for this. It is the one that looks a little bit wider. So I've made a point here that the VIX has much larger variance compared to the others. So if you look at this one here, okay, this VIX has got much larger variance than that of the rest. The rest are all tiny, but the VIX is very, very larger variance. In other words, there's a larger disparity, of the data set. And that is one observation you can see. If you want to get a sense of the interdependence of the data, we can now look at the scatter plot matrix or the correlation matrix. They are two different things, but they serve the same purpose. So this is a command that will give you the scatter plot matrix. If you run this, you are going to get a scatter plot matrix of the data set. Guys, you check some papers, you see them that having the same thing that you are seeing here. Okay. This is a clear scatter plot matrix. Remember, you have one that is your variable in question. Our variable in question is this one here, a MSFT, Microsoft predicted. And this one, when you look at this column, it tells you that there seems to be some positive correlations and some negative correlations for MSFT with some of the variables. I decided to generate an actual correlation matrix here in America. This is the one that is here. And when you print because the heat map here is not showing much. Okay. When you look at the correlation matrix here, it gives you decimals. It gives you a lot of decimals, so it brings home the point. So what is observation? If you check carefully, you will notice that some correlations of the MSFT, is showing positive correlation and negative correlation. It's not so high. For example, look at MSFT predicted. Yeah, they are not so high at all. Okay, some are depicting negativity, some are depicting positivity. So basically, it's not much. There's not really much. Okay, when you come to this one too, it is 0.7, 0.5, 0. Unlike some here that are 0.07, 0.05, and I don't know. So there's some sort of correlation, but you see negative correlation of many asset returns versus the VIX. So if you check this one here, it's having negative relationship with almost every variable, except, well, not all, but most of them. So you see that it is having some negative relationship, which is very, very intuitive if you understand the way the volatility index actually behaves. So this is just to give you an initial mark of how this data works. The next thing is to visualize the relationship between all the variables in the scatter plot matrix. There are two ways to show your scatter plot matrix. One is you don't want to show in the previous class I said it. If you indicate that corner is true, okay, it is going to, okay, it's changed the thing, but it's okay. It's going to show you not the upper diagonal. Okay, the right diagonal of the data is not going to show. But this is another way to see whether there's a positive relationship or negative. Now look at it carefully. And you see that these ones are showing negative relationship. But look here for our dependent variable. This is our dependent variable. This column here. And it doesn't show much of a relationship, to be honest with you. It doesn't show clearly. Like if you look at, this one is perfectly correlated with that because we said it's the same value we have collected. But when you look at this, there's not much relationship that is being exhibited there. All the same, we have to proceed and look at what is going to happen. Okay. I've said that here. Otherwise, we don't see any special relationship between our predicted variable and the other features. Okay, Now, we are ready to do some time series analysis. I said time series because we are dealing with time. But before we do that, we need to show the data set. Okay, so this is once again the data set. It will load the data set again. Did this thing show? Yeah, the graph showed. It will show the data set, and this will show the tail of the data. Now, whilst the data is loading, I'm going to, okay, so what we are going to do here is to show how the data looks like over time. Okay, we call it seasonal decomposition. In fact, if you have learned about seasonal decomposition tells you that there are 4 ways or 3 ways to look at your data, a time series data. So this is a seasonal decomposition. So first look at this. After the data is shown, this is the seasonal decomposition. So in this seasonal decomposition, run yours. You will notice that this is a daily data, okay? And because it's daily data, the period is 365 days for yearly seasonality. If you use this command to decompose a seasonal or to undertake the seasonal decomposition, it will tell you for our predicted, just for the predicted data, it will tell you how the data looks like. It will tell you that there is a trend. It will tell you whether there is seasonality, and it will also give you the gap between the two of them. In fact, the first one on top, it doesn't have the name, but the actual name is observed, the actual data that we have. And then in case there's a trend here, you will notice the trend of some of the years. When you look down here, it's supposed to show the year, okay? It's supposed to show the year. Unfortunately, it doesn't show the year. So there are some few things that have to be adjusted for it to see the years. This is another level. Run this and then you see. This is another level that is also supposed to show the year. This was just to add colors. The good thing is that it tells you that this is observed data. This is how the data is trending over the years and how it is seasoning over the years. By the way, the seasonality tend to agree with the observed. And then the gap between them is the residual. Okay. Again, that one too doesn't show the timing. But again, I'm not interested in the years. I'm interested in how the data itself is looking. And when you look at the data, you see that there's a general upward trend, okay, of the return series. And this can be attributed to a large run-up of Microsoft, stock prices in those periods. There is more positive daily return, data point than negative. If you look at it here, the bottom half of the data here is the negative section, the bottom half. Okay. The same thing when you go up here, bottom half. Okay. The same thing when you come here, bottom half. You see the majority of the data are in the positive domain than in the negative domain. And this is a time series, and time series plot is not a stock price, but they are the returns. So we are plotting the returns of the stock. So if you check the trend, well, the trend is mild. Okay. If you check the trend, this is a trend line, is mild compared to the stock price series at the top itself. Yes, Seth.
Yeah, so I just wanted to get clarity of the terms, right? You are saying the returns of the stock and then the stock price. When you say the returns, is it the price gains or losses that I want to understand, say?
Exactly. So the price of the stock, when you put a stock online, it already has its price. Then whether you gain more or you lose, that is a return. So if the price is 2 cedis, that is a price. That's a price you go with. If now that you've taken it there, you now get 4 cedis. It means that you've gained 2 cedis. If the next time you get 3 cedis, you've lost 1 cedi from the 4 cedi. So whatever is happening, there is an original price And things are either moving up and down the original price or maintaining the original price. Those are the results.
Yeah. So, which of the features is representing the
The
gain or
original
loss?
one is the one here. The original one is this one here, the blue one.
Okay, sir.
And that original one will behave in 3 different ways or 2 different ways. The trending and then the seasoning. Okay. And the trending and the seasoning are showing us. So this trending and this seasoning, they come up together to show how the observed has behaved. The gap between the trending and the seasoning is a residual. And trust me, when you look at the data carefully, you see that the residual seems to be behaving the same way as the observed. Guys, I don't know, but you guys must have been taught time series. Or you've not been taught time series?
No, sir.
They'll teach you, don't worry. They'll teach you. Anyway, that's why I wanted to actually let you guys do more presentations here. But I said there's a link I'll give you that will give you all of these easily. It's a very, very simple thing. You see, the way stocks behave, when you take a particular, when you show a particular stock on the market, it will trend. It will behave in a trending fashion. It will also behave in a seasonal fashion. Okay. And then there's even another fashion where it could behave. And at the end of the day, you would deduct the way it is trending and the way it is seasoning, and then you will get a residual from it. And normally, the residual, the outcome, is what you want to be smaller so that you'll be able to now have more confidence in your original one that you have. That will also determine whether you should invest in it, given the way it is showing. So when you look at the components of a time series, that is what it shows. And in this very example, if you look at the trend may show up in the bias terms. And when we go and run the model, you will see these things. The residual, by the way, depicts that white noise or the errors that will happen between the trend and then the seasonality. But if you look at this, if you look at the residual, you check the residual here carefully, it is looking like that of the observed. If you check, for example, look at this one here. Okay, it's the same thing, dipping down here. And then you look at these 2 sharp rises. Okay. And then there's a third one. It appears these 2 sharp rises and potentially the third one. Okay. Then towards this end here, you see that there's a similar one there. So clearly, it just shows that there's a very small, residual or white noise thing, over the entire period. Again, this is just to show you what is called a picturesque understanding of your data. It doesn't mean much except when we are going to run it and test for possible autocorrelations. Okay. Now, we need to do feature selection. Feature selection basically means that the features are too many, so let's drop some of them. But when you look at our data, how many is too many? We have only 9 variables. I don't think there are many. We have 1, 2, 3, 4, 5, 6, 7, 8. Forget about the dependent variable, which is this, 9, 10. So we have 10 variables. They are not that many. But if the features are many, then we can drop some things. So I've made a point here that the data obtained for this study is relatively clean. It doesn't require further processing. Feature reduction might be useful here, but given the relatively small number of variables, we will keep all of the variables. We are not going to delete any variables. So don't worry about any feature selection. I show the name of the data again, and this time we are going to run our model. Okay. we're going to run our model. Now, ideally, if we were to do feature selection, this is what we would have done. We would have used this one to do our feature selection. Would have first defined the features and the target. And look at something here. In these features and the targets, we would remove the date. Because we would also remove, who is disturbing like that?
Sorry.
We would also remove the dependent variable because we are interested in the features, which is the independent variable. Okay. So we'll do that. I've indicated here that since stock markets returns are continuous, we'll use the F regression or mutual info regression. We will remove the date because we don't need the date and the target variable because to be able to get our features. So if you have learned a little bit of feature selection, that is what we are basically doing. We'll print the feature scores, run this and print the feature scores. And when you print the feature scores, normally, the most important feature will have a higher p-value and a lower score. And so if you check here, the most important feature would have been, the exchange rate between the yen and the dollar. In this case, that is the most important feature. However, don't forget we've already said that we are going to keep all our features. Sorry, what did I say? The most important feature is the one with the higher score and the lower p-value, okay, which in our case is a MSFT DT. So this is the most important feature. And then the DEX, the exchange rate between the yen and the dollar is the least important feature. Ideally, we would have dropped them, but like we've already agreed, we are going to keep all of the features. Okay? So we are keeping everything. In other words, we are keeping everything for the purpose of our analysis. And now we are ready to do our analysis. Who has been able to get the feature scores? Who has run the model to get the feature scores? Let me see the hand. You got to be moving along with it. Somewhere you got it. Yeah. Who else? You got to be working along with me, and you have to tell me when you are stuck somewhere, because you would do similar things like this. Yes, Isaac. What's your question?
Look, I was only indicating that I've also been able to do it.
Good. I mean, if I were you, I would have run all of these things even whilst I'm talking, so that you know where the challenge is. You don't need to wait for me to ask. Look, the most important thing for today is evaluating the machine learning algorithms. Okay. And our time is up, so I'll just talk about the training and the splitting and the evaluation method. Just give you a bit of the theory behind, and then tomorrow we'll wrap that up. So here's the first thing to note. We will split our data into training and testing chunks. You know this already. Now, why? Very good to partition the original data. The original data is almost 4,000. Partition it into training and testing set. Now, the testing set is a sample of the data that we hold back. We don't include it in our analysis. We will use it right at the end of the project to confirm the performance of our training model. Now, the testing is the final test that gives us confidence on our estimate and the accuracy on unseen data. Because if whatever we have done is replicable in unseen data, the testing will tell us, because we didn't use the testing anyway. We'll use 80% of the data for training and then the rest for testing. Now, here's the important part, because this is time series data. These are daily returns. In time series data, the sequencing is very important. The order of observation is very important. So we don't just distribute the data into training and testing. No, we select an arbitrary split point in the ordered list, of the observations, and then we'll create 2 data sets. What do I mean? This is what I mean. So if we load the data, and this is the loaded data here, okay, you load the data. I've put something here called past dates. This tells pandas to convert the columns that is named date. And if you can remember, we have a column called date. Okay? It tells Panda to convert that column from a string to a proper date time. Because you see, pandas has to know that this is a proper date time. Up here, it looks like date, but it's not date time. It has to be in a proper format of the date time. And that is what it does there. So that is why we do this past dates. Then you also have the day first being true. Remember the drop not available, we know what that means already. Now the day first being true, it can be true or it can be false. False is usually the default. What it's going to do is that it's going to interpret the date into month first format. So it's going to be month, day, and year. So for example, if you have 2025, it's going to be like, today, May, which is 05. So it's going to be 0510. So the 10 will be the day, and then the 2025 will be the year. So it is month, day, and then year, not day, month, and year. Okay. Now, if you do true, like we have done here, it will interpret the date as day, month, and year. And because we have done true here, it's going to be like that. Now, let me show you something here. So you can see that this one here, it was month, day. Sorry. It's, I think this one is already done already. It's day, month, and year. Day, month, and year. So that's the same thing. That is going to continue. Okay. Then the next thing is this one. It will create an index, which will set the date as an index. So it will remove that column. If you check up here, you have 3, 8, 9. Okay, it will rather use the dating to represent the row names instead of using numbers to represent the row names. It's going to use the date to represent the row names. Okay. Then you have drop where the target is missing. So if there is the target variable, Microsoft predicted if this is missing, the drop NA will drop it. And then you have the features. So all X will be put into 1. So anything aside the MS predicted is going to be classified as an X variable. So you see that one here. So you might look like this X2 is like the dependent variable. No, it's not. This one says that drop anything that is, drop the column which contains this. So X will be anything else that is not the dependent variable. And of course, this is a dependent variable, the target variable. Okay. So you have Y being the target variable, which is a Microsoft predicted, and then everything else is the independent variable. Now we are going to do the splitting. This splitting requires you to choose a validating size. So this is interesting, guys. This is the part which, if you have not learned, and from the way you guys are talking, you've not yet been taught that part. Now, in here, you have a certain percentage validation size. Okay. Normally, you would expect that you rather give you the 80%, but no, you rather give you the test one. That percentage, that 20% of the data used for the testing, because testing is the same as validation. The size of the validation or the testing is 20% here, which means that the rest will be the 80%. Now, what about the train size? Well, the train size is here. This This is an interesting command which converts the results to an integer. But what does, so you can see that the int here is an integer. And the len x here will tell pandas that the total number of the samples in the data set. And in this case, these are our independent variable. This will be multiplied by the 80%. 80% is the 1 minus the 0.2. Okay, so this is going to be the train size of the data. So X train, X test, split, all of this, you're going to be able to now have your, so this command is actually giving you a complete percentage for the data, a complete percentage for the testing. And now we now can allocate them. All of this column here, okay, you are going to take the rows from the start all the way up to the train size. Okay, remember the train size, we've indicated it already. Okay, the portion of the 80%. Okay, and then it will use an integer location based on the indexing to get the entire data set for the training. The data part that will be used for the training. For the independent variable part, you do the same thing for the dependent variable part. We've already said that the order of the variable must be watched. So in case of the y, the order of the y must match the order of the x to avoid anything. So if you check carefully, we start all the way from 0, to the end, okay, to the end of the variable, which is the dependent variable's end. And then we'll do the same thing, also starting from the 0. So they are very, very important. And I've put a note here that in case the data is not dependent on time series, then the train and the test split should be done based on sequential sample. That is one after the other. Okay. Now let's show the data after we've done all of the train splits. And there you go. So you can see that now it has organized everything in a very nice data frame. The data has been made ready for the evaluation. Now you are ready to do your analysis. Now what we'll do next time, we've got some 15 minutes, right? And now we don't. We have some 15 minutes.
Yes, sir.
Okay, good. So the evaluation. Now, cross-validation, all that I've said, you can also do what we are going to do cross-validation straight away after we've done the evaluation. So I want to just briefly give you an idea of cross-validation. Now, what I mean by I'm going to do cross-validation immediately, that after we have done these things, you see here, we are going to do the modeling. After we have done the modeling, we have to check which one is the best. That's what I mean. We have to check which one is the best. But, so we're going to do this one, and you can see that we are doing cross-validation here at the same time. But I'm going to explain cross-validation a bit of it before. But we're not going to do this today. We're not going to do this modeling today to get the result. This will give you all the commands for all the models. But the cross-validation will actually help us to know which one to select. Whether we should use the lasso, we should use the elastic net, the k-nearest neighbor, the decision tree, support vector regression. Any of them, it will tell us in the context of the cross-validation. So that's why I want to just give you theoretical overview of the cross-validation for next time. What is it? Cross-validation is very useful for robust model evaluation. You can use it to evaluate how well a model generalizes to new unseen data. So when you do a model, that's why the 80%, 20% rule is very useful. If you run the model on the 80%, you want to generalize it, but if it can work perfectly on the testing data, then it's generalizable to other ones you don't see. That's the whole idea. So that is cross-validation. It's like you are checking, you are validating whether what you've done is correct. How does it work? You split the data into multiple subsets, the original data. You split it into parts. In fact, sometimes you're going to see one of the key approaches called K-fold. And the K-fold here means part. The fold means parts. So you split it into parts. You train the model on some of the subjects and test the model on the other subjects. The process will be repeated multiple times to get a more reliable estimate of the model performance. It's like bootstrapping. And there are several methods of doing cross-validation. The commonest one is the K-fold cross-validation. There is also the leave one out cross-validation. There's a stratified, there's a holdout, there's a repeated, and so forth. But let's just focus on the K-fold. The K-fold cross-validation uses K minus one fold, that is K minus one parts for the training. That is 90, in this case, K is 10. And you're going to see very soon why K is 10. So you use 10 minus 1, which is 9-fold for training and 1 fold left for validation. The K can be 5 or can be 10. But like I said, we'll use the 10. Okay. Now, to optimize I've put it here, this is a digression. To optimize the various hyperparameters of the model, we are going to use the 10-fold cross-validation. Then we'll recalculate the results 10 times to account for the inherent randomness of the data. We'll evaluate each algorithm, not today, tomorrow. We evaluate each algorithm using the mean squared error. That is one means to check whether the model is good. The mean squared error is not the only one for evaluating the model. There are other ones. But then the mean squared error gives an idea of the performance of the model. So apart from the mean squared error, the other ones like root mean squared error, okay, mean absolute error, the usual R square that we have, the MAPE, and then the MINE, the median absolute error. All of them, they have their own advantages and disadvantages. For example, the mean squared error is good, but it's sensitive to outliers. The median absolute error is robust to outliers. So now why K equals to 10? We've said that the number of folds is 10. Why? First of all, the data set will be split into 10 equal parts. The model is trained on 9 of the parts. It's validated on the remaining 1 fold. And the process is repeated, meaning that each fold, each part will act as the validation set once. So I'm sure you guys understand it. So if you have something like this is the one, oh, this thing is not showing up. This thing is not showing. Oh, okay. Okay, so if you have 1, 2, all the way to 10, we'll take 1 as a validation set. And then we'll take the other 9 as a training. When we finish, we'll take 2 as a validation. Then we'll go and add this 1 to the others and take that 9 as a validation. Then we'll take all the way to 10. We'll put 10 out and we'll do 1 to 9. All of them, and they do the whole process 10 times. That's the whole idea. That's what exactly I mean by the validation. But why do they 10 times? And here's the point. Because the 10 will balance the computational cost and it will give a reliable performance estimation. I mean, you guys would know that when your children are counting, they count 1 to 10 and they pause there. Okay. So that's it. So that's why we use the 10 in that regard. As for the seed, and you're going to see we choose the seed simply ensures that the data splits are consistent across the rounds. So seed is like when you choose that 42, to avoid
random state.
Exactly, to random state to avoid, heaping up all the time. All right. Then the last bit there is that the score. Remember, we are going to get the score for each model when we run. And we are going to use the mean squared error. But then there's something about the mean squared error, which is the reason why you cannot use exactly the mean squared error, but you should use the negative of the mean squared error. and I've made that point here, that to avoid confusion, to compare it with other models, we invert the mean squared error. Why? And this makes sense, because lower mean squared error is better. You see, the word is error. Error means a lower error is better. Okay. But scikit-learn, what it does is that it gives you negative of the mean squared error, so that it will be in consonance with the higher score being better. Because normally the word better is when something
is high.
Thank you. You understand what I mean?
Yeah.
Yeah. So, otherwise, it's just a matter of just taking an absolute value, basically. All right. So that's it. And now we are ready to run the model. So these are the models we are going to be running. Okay, we'll run this model. We'll run regression and tree regression. All these regression models we are going to run. We'll run all these neural network model, okay, which is the multiple layer. And then we'll run the ensembles, both boosting methods and bagging. They are all here. The boosting methods include the adder boost. Okay. It includes the gradient boosting. The bagging method includes random forest and then the extra trees. Now, the steps you take are as follows. So I'm going to show you these things that you're going to see plenty down here. These are the, so once we have selected all the models, which you're going to see down here, we'll loop over each one of them, okay, which is what we've done here. Okay, select, I decided to really take my time and do these things and loop over each one of them. Then we'll run the k-fold analysis and then run the model on the entire training and the testing data set. All the algorithms will use the default tuning parameter. So we are not going to apply hyperparameter tuning. Okay, we're going to leave them as it is. Like in case you have the microwave and you normally, instead of tuning it to 5 minutes, you just press something and that is the default all the time. For example, if you have the one that I have, that is 30 seconds. Once you press the thing, it's 30 seconds. If you press it many times, it's multiple 30 seconds. Okay, so for each one, we'll calculate the mean and the standard deviation of the evaluation metrics, and then we'll collect the results for comparison later. So there you go. You need to have these things and everything we have loaded before ready, and run this. Run this. Okay, these are all that we have explained. Okay, the k-fold, the splitting, the validation, fitting the training model. These are the residuals. This is a training of the model, creating the mean squared error, evaluating what you have on the test model, okay, and then seeing the results. At the end of the results, you want to show the mean and the standard deviation, printing the mean and the standard deviation together with all of the results. We'll look at this tomorrow, because that will be the main thing for tomorrow. But please go and read it before we meet, because you all have this. Look at this. Look at this. We are going to compare the models, okay, for each one, and then we'll make a decision, and then we'll compare it. Here you will see it properly, because here I was able to bring all of the timings into the picture. You see it all, and then we'll check how everything works in the end. Ladies and gentlemen, that brings us to the end of the entire Kabudo.
Kabudo.